level. Good morning. Everybody doing okay? I'm going to assume that's for the donuts, and I'm okay with that. How are the donuts, by the way? Yeah? All right. I hate to do this because this feels like exclusive, but like, so raise your hand if your favorite donut is the Meyer Lemon. You're all dead to me. Fritter? The chocolate ganache? Yeah. Passion fruit? Yeah. Olive oil for the vegans? Yeah, you just raised your hand twice. I saw that. All right. And did y'all have fun? Huh? Yeah, no, I did. I said fritter, not apple fritter, because I'm not sure if it was apple or pear. But how was last night? Did y'all have fun at the parties last night? Yeah. Yeah, I might have set a record for like most number of sponsor parties. That was actually pretty cool. Okay, just a few notes before we get kicked off this morning. Again, a reminder: please wear your mask when you're not at the podium speaking or drinking or eating. No drinks or food in the theater. If you haven't already, please enjoy the coffee outside. And, a reminder, I assume you probably already know this because I announced it yesterday and I don't see any suitcases in here, but in case you missed that, we do have bag check at the box office today. And, if you happen to stay around to the end, and I hope that you do, we have some prizes to give away. So make sure to hold on to those tickets that you gave half of for the monitoring socks. And yeah, I think that's it. Any questions before we get started? Cool. And anybody wants to talk about Framework Laptop, you know where to find me. All right, we're going to start off day number 3, last day of Monitorama PDX 22, with an awesome speaker. Can we get a very nice round of applause for Dudi Cohen?
Hey, good morning, everyone. If anyone has a hangover from yesterday, please let me know. I'll talk slower. And I anyway try to do it as short as possible. So a few words about myself. My name is Dudi Cohen. My real name is David, but nobody calls me that. I'm Rookout's VP of R&D. I basically manage our R&D. And I'm a debugging addict. I love solving problems. I love solving my employees' problems. I love debugging my own code. And in Rookout, also, I love debugging our customers' code. But that's another talk. I'm also a low-level geek. If you want to talk about reverse engineering, bytecode manipulation, whatever, just ping me later on. A few words about Rookout, just to give you all the background. We're doing dynamic observability, which is quite new in the observability area. We allow our customers to collect data dynamically in real time from production, from staging, wherever they want it. Again, if you have any questions about it, talk to me later. So I want to share with you my small journey investigating tracing. As my work in Rookout, apart from managing the R&D, I'm also meeting customers. I'm meeting potential customers. And about 2 years ago, everybody started talking with us about tracing. It was tracing that, tracing there. Do you have tracing? We need tracing. And we try to understand, I try to understand, what are they talking about? Why do they need tracing? Do they know what they need tracing? And I mean, we had tracing in Rookout. All of our backend is instrumented with tracing. We use tracing. But it seemed like the crusade for tracing, or the hype for tracing, was really a success. So I tried to understand, why are they talking with us about tracing all the time? So for most of us, when we're talking about tracing, we're thinking about something like this. An amazing system with a lot of data that allows us to know everything everywhere about our application. And that pretty much means that when I see a request going in, I know where it comes from. I know every step of the way what happened with my system, what happened with my requests. If I had an error, I know exactly where that error happened. I know latency. I know everything. I know everything about everywhere. And that's the promise of distributed tracing. But when I started to ask a lot of questions, also and in how we handle and how we look at tracing, I understood that it's not really always acting like that. And I try to give a little bit background about tracing, as far as I know it, to start and talk about tracing. So nowadays, when people say tracing, they actually mean two things. And to be more exact, the two things are very different. The first is request tracking. I think most of us know what request tracking is, but I'll give a brief about that. And the other thing is the observability tools and the techniques that we use in order to have tracing. Both are super important, but obviously they're different. You know, back in the old days, when we had only one instance, one application, when you had a problem, you had an exception, and in that exception, you had a stack trace. That stack trace was the flow of the code until something happened. You would have a problem, you would look at the stack trace, and immediately you would understand what happened. And nowadays, when we don't have only one application, one instance, we need the cross-service request tracking. And that actually helps us to understand what is going on with our microservices. Let's say that I have something stuck in the Square microservice. There are at least 3 options of different services trying to send requests to that microservice. I gotta have request tracking in order to understand what exactly is going on. Who initiated the problem? What is the origin of it? So basically, when we're talking about cross-service request tracking, you're talking about having the stack trace of the entire system, having the stack trace of all your microservices. And the other meaning of the word tracing, which we use a lot, is actually those techniques and those tools that we've been talking about in the last 3 days. It's Jaeger, Zipkin, Open Tracing, Open Census, Open Telemetry. I would really like to think about these things as structured logs on steroids, with a little bit of metrics, a little bit of sprinkles of a lot of metadata, and all of these tools are amazing, but they are not all the time very easy to adopt and to start using. Now, the reality of tracing, as far as I can see, is unfortunately there are too many competing standards and technologies. Even here, when I think most of the people here in the room are observability enthusiasts or experts, being in the first day of Monitorama, the day started with the observation that OpenTelemetry isn't production ready, and 2 hours later, Steve tried to prove that wrong. But the matter of the fact is that right now, if I want to start using tracing, I will take a look at all of those competing standards, and I will try to ask myself, do I need to use open tracing? I mean, open tracing is stable. It's been there for a long time. I should use it. But no, there's open telemetry. It's new. But is it stable enough? Do I need to use it? It's very, very confusing if you're not like a super SRE expert or monitoring expert. And the next thing is that the paradigms are very, very complex. When I want to come and solve a problem, let's say that I'm a developer, I want to see information that I understand. I want to see things that I know what they mean. A developer that looks into his system and starts seeing things like a trace ID, a span ID, a span, a parent span, a baggage tags. What does all of these mean? And these things are complex. If the day-to-day that you do is not only monitoring, you gotta learn and understand what these things mean. And of course, if you want the promise of knowing everything, you have to pay money. If you want to know everything everywhere about your systems, you need to pay a lot of money. You need to collect a lot of data. And that's very expensive. There is the option of sampling, but if you're starting to sample the data that you get from tracing, then the promise of knowing everything about everywhere that's happening is a little bit broken. And the next is that tracing is hard to adopt. I mean, writing manual instrumentation across all your microservices is not an easy thing to do, especially if you're a polyglot and you need to write that instrumentation in all kinds of languages. There's, of course, the promise of automatic instrumentation, which is really amazing and really, really cool. but it's quite daunting. I mean, I'm going to let someone else change my code in real time. It's a bit scary, and that's my day-to-day job. I change people's code in real time. I know that when something fails, it hurts and it's dangerous. And I'll say a few words later on about automatic instrumentation. Now, don't take my word for it. When you're talking with professionals and people that actually solve the problems, especially engineers and developers, when you ask, what is your go-to tool? What are you looking at? What helps you to solve your problems? Tracing is lagging way behind. And it's not only because not everybody have adopted tracing yet. The information from the server isn't only about where is tracing available or not. It's about whether you use tracing in order to solve your problems. And tracing is lagging way behind, while metrics and logs are the go-to tools. Now, do we really need to collect so much data? What about all the carbon that we are emitting when we are sending all those tracing all around the network? Now, I talked about a little bit about the disadvantages of tracing, but let's talk about logs. The amazing thing about logs is that we really, really like them. We don't really like to pay about their cost, but we really like them. And why is that? Because they're simple and very, very predictable. The first thing that you do as a developer is write hello world, and there you have it, you've written your first log. They're easy to use. There are actually things written by humans for humans. Humans are writing logs with the target that humans will read them. And you write them very descriptive, and you know that if you have a log line in your code, and that code runs, you will see that log line eventually in the end. So they're very, very predictable. The instrumentation is easy. I mean, all you have to do is just pick some sort of a popular logging library and just use it. There are not many bad options nowadays. Of course, if you're very, very masochistic, you can also just write everything straight into your console without using a logging library, but that's something else. And of course, the analysis is very easy. Because humans have written logs for humans, it's easy to understand what's going on. And of course, if you're actually using structured logging, then you'll be able to index your logs and properly query them and analyze them. And what do we like about metrics? Well, they're numbers. They're very, very easy to understand. There isn't a lot of complex math there, and we really like numbers. I know that 1 may be low, 100 is high, and I can easily understand what's going on with my system. And of course, you can take those graphs, shove them into a graph, take those numbers, shove them into a graph, and immediately understand what's going on. Graphs of matrix are usually really an image that is worth 1,000 logs, or maybe 1,000,000 logs, I don't know, depends on your system. And they're easy to learn, they're numbers, we all know numbers. And of course, they're very, very cheap. All you're doing is actually taking a small amount of data, taking numbers, and shipping them away. So if we like metrics and logs, why do we need tracing? Why traces came into our life? Well, it's because logs and metrics weren't enough. We always try to search for more data, to understand more what our application is currently doing, understand what is happening in our system. But ever since traces were introduced, both logs and metrics have done a long way. They have evolved. And during the last 3 days in Monitorama here, we saw a lot of examples for it. And we need to remember that we don't need to run and immediately get tracing. We can solve a lot of problems with metrics and with logs. And I'll take a few use cases and see how we can actually solve them with metrics and logs, and we don't have to run and adopt tracing immediately. Okay, so the first problem that usually we're talking about when we're talking about tracing is the lack of context. What's context? What context is understanding the circumstances where the settings of an event happen. Who did it, what did it, when did it, I mean, a context is actually understanding if you see maybe a failure, you want to understand what caused that failure and where it happened. Now, how can you solve a context with tracing? Well, that's basically the promise of it, as I mentioned. But where do we see tracing lacking when we're talking about context? Well, first, I talked about the high costs. It's very, very expensive. Sampling is, again, if you're sampling and you want to understand everything, the context of everything all the time, then sampling misses the goal. And there are complex data structures. As I mentioned, as a developer, if I want to solve a problem, I want to take a look at the information that is very, very relatable to me. It's not easy to write a standard like OpenTelemetry. There is a lot of time invested in the naming conventions of the components, the naming conventions of all the items that you're collecting, and we want to make everything very, very, very familiar to people who try to use the information. But showing a developer information such as a trace ID or a span ID is practically the equivalent of me walking around Portland, asking a stranger if he can help me out and tell me where I am, and his answer will be a GPS coordinate. If I would have had a GPS, I would use a GPS. I want something that I can relate to. I want a street name, maybe a city if I'm that lost. So we need the information to be very, very accessible to developers. And when something is burning, I don't want to learn new information. I want to have information that is very relatable. So the next issue is the non-applicative context. Trace ID, span ID, that things are not part of my application. I don't know where they came from, especially if I had auto-instrumentation happening. Auto-instrumentation is very, very amazing, very, very cool, but auto-instrumentation assumes a lot of things. For example, let's say that auto-instrumentations bring me the information about the HTTP request. So I will see http.request. I will see that information. But maybe in my application, that thing isn't called HTTP request. Maybe some other developer, or maybe me, gave it another name. Do I need to really learn what exactly is the equivalent of an HTTP request in my application and in OpenTelemetry? So these things are very challenging. When I want to look at the context, I want something that I can relate to. So we have to use more logs. The first thing about using logs in order to get context is to write high-quality log messages. Log messages such as here, there, or if you're seeing this, there's something horrible happened. Those are logs that make no sense. You have to invest time in order to think about you waking up in 2 a.m. and looking at logs and trying to understand where and what happened. And of course, you have to include relevant variable values. Logs also have the possibility to include values of variables in your application. Things in your production are not behaving different from dev and staging because it's in production, unless you have bit flips and your CPU has problems. But things are acting different because production processes different data than staging and dev. So you have to get information about what data is your application currently processing. And the easiest thing to do to get context with logs, and actually a lot of people don't do it, is build log enrichment. It's very, very easy to automatically insert information that is very much relatable. A file name, a line number, those things are golden when you're talking about context. And if you don't have these things, you gotta have them. And of course, as I mentioned, you have to use structured logging. Yesterday, Joy talked about it. It was written in bold, black on pink. You have to use structured logging. If you're not using structured logging, you're doing something terribly wrong. If you're using structured logging, you can index your logs, you can easily analyze them, easily aggregate them. And of course, you can actually implement cross-service request tracking with your logs. It won't be as robust as using full-blown tracing, but you can actually do it. If you're using structured logging, you can add the source address, destination address, and even unique IDs that will allow you to track your logs. Now, there are real-life examples of adding context into your logs. A few of them are MDC in Java, map diagnostic context, which is pretty much used for that. You can just add something to your thread storage, remove something, and almost all Java logging libraries know how to pull information from your MDC and log them into your logs. And in context, you have the concept of the context object, which is a part of a lot of API calls. I use this a lot of time in Go. I think all Go developers use context. It's idiomatic. It's almost part of the language. And any logging library that you use in Go will probably be able to easily integrate and get data from your context object and write that down. And in Python, we have logger adapters, we have filters. Almost every language has its own alternatives. But what about across services? I mentioned that you can sort of add request tracking to your logs, but it won't be as robust as tracing. So the main questions that we actually need to ask ourselves, whether we really need it all the time. Whether we really need to burn a lot of carbon and get those tracings all the time. Do we really need them? Do we really use them? Now, as I mentioned, tracing promises you a stack trace of your microservices. And try to think about problems that you see when you have a stack trace that are a part of an exception in your code. How often, how many times do you really look at your stack trace to see what happened, what are the steps that has led to that exception? Often you just look at the exception and you pretty much know what happened, because a lot of times our code is very deterministic. Our code doesn't always surprise us. So sometimes you need to really ask yourselves whether I really need cross-service tracking. If I had problems in my Square microservice, yeah, I need to understand who sent what when. There are at least 3 microservices that can send requests to the Square microservice. But if I have problems in requests sent to the Circle microservice, well, only the Square microservice is sending stuff to the Circle microservice. So even if I have problems in the Circle and I have full-blown tracing, I won't really look at the tracing information. I will just know that everything was sent from the Square. So we need to understand how adventurous is the flow of the requests in my microservices. Who can initiate a flow? What can initiate it? Or maybe even when will things be executed? If I know that that requests are sent in a specific time, that I will know who sent it and when, because of the timestamps. So I don't really need request tracking all the time. If there are places that I don't need request tracking, I don't really need tracing for that. And the big problem that tracing wants to really solve is getting more data. The promise of tracing, of knowing everything everywhere, really counts on having a lot of data. Now, what can we do in order to get a lot of data? Well, first, metrics. Metrics are cheap, we like them, get more of them. Some organizations only use the very basic metrics of stuff like, I don't know, CPU consumption, memory consumption, etc. These are not enough. You can add custom metrics. You can get your application, create some numbers, add them, subtract them, do whatever you want with them, but you can send them out. Those are custom metrics. And because you have created them, they are very much in the context of your application. You will know what they mean. Even metrics like sending out a metric saying that a specific function is invocated, that's also golden, and you can play around with it. So you can do applicative metrics, and we also yesterday saw a really good example of metrics generated from logs. We saw an example of Loki. The fun thing about it is you're anyway sending out logs, and you really want to get more information from those logs. And cooking up numbers from those logs is very easy. And the fun thing about it is also that you don't really need to have those log-generated metrics all the time, because you can create those metrics in your server. You don't really need to redeploy in order to change how that happens. And when we're talking about logs, logs are expensive. When we want more information from logs, we just get more logs. But volume is different than value. We want to get the right logs in order to understand what's going on. And there are several techniques to do it, to get the right value, and not only by increasing volume. One of my favorite techniques is managing verbosity. When you're writing your logs, you're writing logs in different verbosities. You have the debug logs, you have info logs, etc., etc. Most of us don't run verbosity of debug in production, because that will spam us all the time. You don't want to get all the logs all the time from debug verbosity. But those debug logs are amazing. Developers have thought about them, what will go wrong, and actually wrote a lot of data in those debug logs. Many companies implement their own solution of flipping a switch, choosing a server, and telling that server, right now, I want you to give me debug information. I want you to give me debug logs. And when you're done with collecting the data, you can just go ahead and turn that off back to maybe info verbosity. And there are also several tools that you can actually buy in order to accomplish that. The next thing is cold and hot storage. Yesterday we saw good examples of how Slack does that. And that means that you can just collect logs, ingest them, and you don't have to index them. A lot of times, the money goes into the indexing. You don't have to index them. Only when you will be in a situation where you actually need those logs, you can get them out of cold storage and index them. And of course, you can optimize the volume, remove spikes, drop noisy logs, etc. But the most important thing is that you have to research your needs and act agilely. You don't need to only set up your logs and say, okay, from now on I have, I don't know, retention of 15 days. This is how my logs work. You need to understand which logs you use most, what types of logs you don't use, and you need to all the time change how you consume and how you send your logs. The last use case is investigating latency. Tracing does that amazingly. I mean, if you know what's happening every step of the way and what is the time step of every step, you can investigate latency in a very granular manner. So how can you do that with logs and metrics? Well, it might sound funny, but you can just use the timestamp of your logs. Of course, it's not as amazing as tracing, but you can just start with metrics. And if you have the right value, the right information from your logs, just take a look at the timestamp of your logs, subtract them. I know sometimes it seems like a very, very funny way to do it, but it actually works. And developers that even use tracing do this all the time, but it really depends on the quality of your logs, whether you have logs in the right places or whether you got the logs from the right place. There are also solutions for live profiling or demand profiling that you can use. Now, to recap things, I don't hate tracing. I hope you don't think that. Tracing is awesome. It's really, really amazing. But we really don't need to get tracing because all of the cool kids are using it. Not everyone is Slack or Uber or Facebook. Tracing is expensive. And we need to use tracing only because we understand that we need it and that we actually know how to use logs and actually know how to use metrics. Now, we love logs, we love metrics. We need to improve how we use them. We need to adapt to them. We need to all the time ask ourselves whether we're using them in the right manner. And of course, the last thing is that we really need to understand how to make tracing more accessible. Yesterday or 2 days ago, we had a talk about making your application accessible to people with disabilities. But we really need to make tracing accessible to people who don't know tracing. And we still have a long way to go. That's it.
right, we've got a few minutes for questions.
Cool.
All right, any questions from the audience? And anything up top? Nothing? All righty. Thanks again.
Thanks.
So I need the folks here to settle a debate for me regarding donuts. I'm already on donut number 2. There might be a third in my future, we'll see. But who here loves a good cake donut? You know, those like great dense ones, show of hands, right? So Jason is kind of claiming that the cake donut is not actually a donut. I disagree with that one, but how many people here have like very strong opinions about, I would say a negative opinion about a cake donut? Really?
Cut the mic. Cut the mic. Cake donut is not a donut. It's cake in the shape of a donut.
Is that wrong? Anyway, we had a conversation much longer than I'm willing to admit about this backstage, so. All right, so who here, I don't want to, like, this is very much a judgment-free zone. By show of hands, who has had 1 donut? Okay, keep your hand raised. Who has had 2 donuts? Yeah, all right, keep them up. Who's had 3 donuts? Yeah, all right, this is bonus round. Who has had 4 donuts? Yeah. Round of applause for the 4 donuts. I'm gonna check later if we want to see who is going to win. I don't know about win, but you know, I want to take a nap after my second one. All right. Loading, buffering. What is loading right now? Try. There we go. All right. All right, big round of applause for Hakan.
Hello. Let's start with a fun fact. In 1893, there was a US Constitution amendment proposal to change the name of the country to United States of Earth. So next time someone complains to you about how American teams, when they win their league, they call themselves world champions, you know, you remind them that it could have been much, much worse. And the relevancy of this will reveal itself at the end, so stay tuned. My name is Hakan, and software engineer at Lyft. We built an alerting system about a couple years ago, and I'll be talking about that. Here's a little peek into the outline. So I want to talk about, being down as a company, your systems. We all try not to be down, right? That's all our job. It's really bad. But is it really bad? I mean, for our users. I mean, it's bad for the company. We're not making money. Obviously, our jobs are at stake. But, so I selected a few examples here, completely random, not to prove a point at all, that it may not be that bad for the users. So, for example, if Facebook, Instagram is down, well, they can always go, listen to music. Or if they're feeling adventurous, they can go outside. If Slack is down, I mean, now it's bad for the customer companies, but the users who are the employees of those companies, they can go get a coffee for 30 minutes if it's down. They can go, load the dishwasher. Or if they're feeling adventurous, they can go outside. And I mean, all these other things, Netflix, Messiah, C-SPAN Plus. So again, they can read a book maybe, or if they're feeling adventurous, I forgot my actual point actually. Okay. So, but Lyft, on the other hand, when we are down, our users are already outside. They are on an adventure. They are trying to, go to their job interview. They are trying to get to their doctor appointment or to their work. So if we are down, it's not just an inconvenience. It's a major issue. And now think about how frustrated you were when you're stuck in traffic. And think about now you're stuck not being able to get in traffic. So that's why alerting is very important for Lyft. So I'll talk about alerting mainly, but of course alerting always comes with a metric system. And most of this talk will be about the alerting system itself, but I will also talk about how we also worked on the metric system and how it relates to it. And most of the cost always comes from a metric system. So if you go back to late 2019, Lyft has been growing pretty fast the last couple of years, and we had a vendor that we were using for our metric needs, and there was an alerting system built on top, which was basically given to us for free. And because of all the growth, we were about at 100,000 alerts per minute, and we were emitting about 40 billion data points a second at that moment. And the cost was quite prohibitive at this point. We were getting close to 8 figures per year, especially if you take into account the growth that we were expecting. And of course, we were going to grow, right? I mean, why wouldn't we? We've been growing every year, and it would take like a global catastrophe for us not to keep growing. But with growth, with the scale, with the cost and scale, there was also reliability issues. We were having issues. Our vendor weren't able to always handle the load. And since we didn't own the thing, it was quite frustrating for us. We didn't really have clear insight into the issues. We didn't really have clear guidance how things were going to go if we keep growing. So we wanted to move away, but to make it easy, we thought that the best way is to decouple the alerting part from the metric engine, metric data store, and then that would make it easy for migration, and it would also make it easy to do migration if you don't like the first time we migrate. So once we made the decision to separate the alerting system from the metric data store, we started looking into the options for the alerting system part. And we were exploring some third parties. Usually it wasn't that easy because they usually don't give you just the alerting system. It comes with the metric engine. And we didn't want to get stuck by moving the whole thing to another vendor and then have the same issues. We looked into some open source. There were some options, but we didn't like what we saw. And we didn't want to, maintain our own fork if and based on and dependent on updates. So we pretty much were set on building the alerting part of the system in-house because we thought we had a clear idea about the scope, and we really wanted to have full control over the software lifecycle in terms of issues and all that and bug fixes, and basically increase our institutional knowledge about these. But of course, as Corey said, I mean, we already had the gut feeling that we wanted to build it, and all this is kind of reasons we came up with, maybe after the fact, right? So I'll let you read this comment from Hacker News I saw a few months ago. So we were definitely at the let's just roll our own, how hard can it be point. And we were hoping that we won't get to the oh crap point. I actually reached out to this person about this code, and they agreed that it's fine to code them here, and they said they still feel the same way. And I mean, it's fine. Yeah, fine. All right, let's keep going with the scope and design. So our scope was to build a system that can work with any metric data store, and preferably more than one actually, both because of doing migration and also later on because we might want to integrate with other data stores, and we want to be able to configure our alerts specifying different alerting medium, frequency, snoozing, again, the metric data store, and different conditions for the alerting logic. And our thinking about the migration was that we would start operating it along with our third-party system until we validate everything about it. So we tried to keep it pretty, determined in the beginning and not allow much scope creep. Existing system. So existing system is pretty simple, right? We just, well, actually, this doesn't show the metric side. Obviously, we're sending all our metrics to our third-party provider, and then they provide us the alerting system as well. And this part only shows how the integration about the alerting is done. We have a big repo that has the configurations for all the alerts, for all the services that we have. And then whenever something is added and removed, we would be basically calling our third party and update the alerts on their side. And then when there is an alert happening, they would call our own pager service, which is basically a wrap around the pager duty and some other notification mechanisms. And that would be it. The proposed system we had looks like this. It seems complicated, but it's not actually that much complicated. So if we start with the top, we would have an alerts database, which is basically all the definitions of all the alerts. And then the alert storage service is kind of like a backend service that would be powering a web app, and it would also reveal an API if other services wants to do certain things programmatically. And it would talk to the metric engines to show what the current state of the metric is of the query of the alert. And the bottom part is the actual the alert evaluation and so on. So we would have a scheduler that would read all the alerts from the alerts database and update it regularly, and then it would schedule all those alerts based on how frequent they need to be scheduled, and then call the evaluator for evaluation of these alerts. An evaluator would evaluate the alerts by checking with the metric engine and the latest state of the alert from the alert state database, and again, it would call our existing pager service if needed. A little bit more detail about the scheduler. We wrote this, actually the whole project in Go, other than the front end, and this is kind of in Go style how the scheduler would work. Scheduler is only one instance, basically, but we wanted to have a few, obviously, backups. So there would be like a few scheduler instances, but only one would be the main scheduler, and the others would basically try to become a main scheduler, but fail most of the time until the main scheduler dies for any reason. So the main scheduler would get the distributed log and then become the main scheduler. And then it would basically have two main functions, the schedule alerts function and the drain queue function. The schedule alert Go routine would wake up every 1 second and schedule all the alerts for that second, which means put them all into a Go channel of alerts, and then go to sleep and wake up in next second again to do the same thing. And the drain queue Go routine would basically run non-stop, reading from the channel, and then based on the alert definition, call, actually, it has nothing to do with the alert definition, it just calls the evaluator. Evaluator, based on the alert definition, calls the right metric engine, and then based on whatever logic it has, based on the configuration, would evaluate, and depending on the state changes of the alert, it would take some actions. Well, more like trigger the actions that's needed. And this is some of the proposed actions that we had in the beginning. I'm not sure if there have been more granularity on these. So how we built it. The So schedule evaluatory part, this part was the part that I was mainly involved in. It took me about 4 months to write this part until we get to the MVP part where we can load alerts, schedule them, evaluate them, and so on. And then I rolled off this project, and another engineer came in, and then they worked on it for about 3 more months until we were ready for migration. And alert storage service, there was a bit more work to do there because of the front end and charting and all that. It took about roughly 6 months, about 2 to 3 engineers on and off working on it. And then we did the migration in 2 months to migrate all the alerts to the new system, and we were done. Isn't that great? So, you have 20 minutes back. Let's talk about migration. Yes, the plan was to do it in 2 to 3 months. And then, however, very, very soon into the migration, we ran into issues, and our metric provider, basically rate limiting us, didn't want us to query them as much as we wanted. So which meant that we had to actually wait until our metric migration was also underway, and that goes through so that we would do it in conjunction with that, which took about 1.5 years. So what we did was service by service migration. We had some volunteer services, some volunteer teams that would go onto our system as well, in addition to the third party that we were using. So for them, third party and the in-house system would be alerting together at first, which was an interesting experience because we found a lot of the time that our system would be alerting much faster. And it's probably because the third party had a lot of noise reduction mechanisms going on that we didn't have, which was obviously a trade-off. But that helped us in the end because since we own the system, we can actually tune it in a lot more in tune with our needs, and we can talk to our teams how they are using alerting, how they are defining their alerts, so that we can still keep the mean time to detection low while not increasing the noise a lot, since we own the whole thing. So when we were running the things in shadow mode, it wasn't easy because the signal was low by definition in alerts, right? You don't get the alerts. A lot of the systems work normally most of the time. So it's really hard to tell when there is nothing on both sides. How can you tell it's correct, right? And I mean, many alerts never actually fire in their lifetimes. And so we had to do a lot of automated and manual checks, and we need to do a lot of checking how the alerts are used and so on, which was actually good because there was an opportunity for checking alert validity. So looking back, I submitted this talk in the beginning of 2020. So I was thinking that in 6 months, not much have changed. I'm just going to talk about the system. We haven't really done the migration by then. But now, 2 years later, it's great that I can actually talk about the whole thing. In the end, the cost issues, of course, again, this is the metric engine cost mainly. Since we have rolled off the third party and are using our in-house metric data store, we didn't build that. It's an open source project, the metric data store. But the infrastructure cost from almost 8 figures, we went down to about low 7 figures. And right now, I talked to the team and they said that so that data store isn't completely great, right? It also has its own problems. About roughly half to a full engineer time is being spent maintaining that data store. But I like to actually say something about this. Like when you are maintaining or working on your own system, that's actually not completely time wasted because that engineer is leveling up themselves. They're learning about it. And they're also building institutional knowledge about how to run this kind of system. Whereas when you're dealing with vendor issues, you're basically talking to them, waiting for their response and all that. So they're building their institutional knowledge. They're making their systems better. But it's not really, your engineers aren't leveling up themselves other than, talking and communicating, I guess, which is a good thing, maybe, I don't know. So let's see, how was it for our customers, meaning the other engineers in the company? They were unhappy during the transition, especially the new UI, because during an incident, all of a sudden, they don't typically look at the alerting system UI unless something is happening. So during a stressful time, they have to look at it, and then they're like, oh yeah, this changed. I don't know how to use this. So that was frustrating at first. We also switched to PromQL for our metric definition during this migration. And there was complaints about it in the beginning as well, because now there was another language that the developers need to learn. And there were some misunderstandings on the syntax compared to the other language that we were using. However, I think it was a big win in the end, because now if you want to migrate to another metric data store, then we don't have to do this, since PromQL is pretty accepted by other data stores as well. And the complaints from the developers were pretty much non-existing after a few months. And overall, we are having a better performance on alert querying and faster mean time to detection. So what about the team, the observability team who built this? I think we were pretty happy, to build a whole system from scratch and see it in action. And I'd like to say something about people talk about 10x engineer a lot. Like, could be just some engineers are amazing, or some engineers are enablers of other engineers. And I think in terms of productivity, most engineers have like a multiple X engineer in themselves. It's just they need the motivation and empowerment to be able to do that. And I think in this case, at least, building gave us that opportunity to really be motivated and level up ourselves. And we actually didn't know Go, none of us, at the beginning of this project. And we built the whole thing while learning Go as well. And when I go back, we didn't do a bad job, honestly. So that's, I think, what's missing sometimes when people are talking about buy versus build. Because they say, okay, engineering time is valuable. Where should it be spent? Trying to integrate something or trying to build something? But that time isn't exactly absolutely equal to each other. Because 1 hour, when the engineer is motivated and focused, that 1 hour will be worth a lot more than 1 hour when they are not really into it, doing something else. And I know this is not something engineering managers or general management doesn't want to hear, but as an engineer, that's how it is. So the new system has been issue-free, which is good for us, for the maintainers. And at this point, for the alerting system side, we are not doing any further development other than regular security updates. There were some feature requests after the migration, which has been completed. So we're not really doing much about it. It's chugging along pretty well. So I think overall, we were able to hit the sweet spot by separating the alerting system and building that for our scale, and not trying to do the same thing for the metric data store. And so I think build was the right choice, looking back 2 years afterwards. But I'll put a disclaimer, of course, saying for now, because when I was preparing for this talk, I saw a talk by a Lyft colleague from 2017 in this conference, and they were describing the logging ingestion pipeline they built, and they were pretty happy with it. It was working great in 2017. However, in 2019, when I joined the company, that was like the biggest pain point of our observability team, that system. Everybody was complaining about it because during that 2 years growth, it got bloated. A lot of new things added into it without good refactoring. And we were basically couldn't wait to get rid of it. So, that's why it seems like we made the right choice, but I don't know how it's going to be from 2 years from now. And if anybody is watching, in 3 years, this talk and thinking, oh my God, this system is not working at all. What is he talking about? Well, I think there's a camera somewhere here. I apologize. And with that, I'm happy to get any questions you have. Can you repeat a little louder?
Sure. How do you handle alerting for the in-house tools you built to deal with alerting?
Yes, that's a great question.
Just repeat it one more time.
Yes, so the question is how do we alert on the alerting system itself? Basically, how do we monitor that? So right now, in the beginning, we thought we would use another third party, or we would use the alerting system itself in a previous version that's deployed in some other infrastructure. But I think right now it's basically we have two separate clusters for staging and production, and staging is watching the production and production is watching the staging, and that's been working fine so far. But I think we should probably think about what I just mentioned for better redundancy.
Here's one right here.
Are you still using one large repo for all of your alerting tools, or are you using your UI to let people set new alerts in that?
Yeah, in the beginning, the idea was UI could be used for that, but and there would be like versioning and such in the UI. But I don't think we followed up with that because it was just too much work to deal with it. And the big repo is not only used for alerting, it's also used for dashboards. It also defines all the dashboards for all the services. So that's, I'm not aware if we want to also make an adjustment on that, but right now that's how it is, yeah.
There was one, yeah, it was right here, yeah.
I assume you on the page of the 100K unit for alerts?
I think we reduced some of that number during the migration. I think I mentioned that we looked into all the alerts or encouraged all the teams to look into their alerts and so on. I think we made some headways in that it's not as much, even though 2 years passed and could have grown. So I'm probably in the same ballpark, but it's less.
Yeah, right here.
I think one of the numbers I saw on one of the slides was 100,000 alerts per second.
Per minute.
Per minute.
100,000 alerts per minute, yeah.
When you think about the database getting, so the external systems that you relied on or the external projects that maybe you don't have control within, was scaling databases a problem, and how did you?
Yes, so was scaling databases a problem for that volume of alerts?
Well, not really. I mean, 100,000 records isn't that much in a database usually for right now. So, and this database is only used mainly to load all the alerts and then do some updates by one system, and then the other system is doing some one-off alerts, obviously based on the usage. But again, we have only hundreds of people using the system in the UI. So it's been fine.
Were there any other questions? Oh, we got one right here.
Thank you. In your build binary slide, you had like third-party services or third-party services and open source. And under both, you had a bullet point about anti-patterns. And I was hoping you could unpack that a little bit and anti-patterns.
So what kind of anti-patterns? Yeah.
Yeah, this was given to you by my boss to mention, and I didn't want to mention because I don't really fully know. But I think his point was mainly that the part about mean time to detection, that third party or open source, they might have some generalistic algorithms to be able to reduce the noise. And he doesn't like that. He thinks that we should limit some of that so that we can tune our alerts instead of trying to rely on things like, oh, if this alert is firing for 5 minutes, then actual fire, and so on. So I think that's one of them.
Yeah, great question. Any other questions? I see, yep, one more back there. Yeah. What metrics data store? Or what volume?
Yeah, I'm not sure about the volume because I'm not in the team anymore, but we are using M3.
And then any other questions at the top? No? One more?
During this project, did you change any part of the data collection or actually getting the data to the metrics data store, or did that remain the same before and after?
Did data collection change?
Yeah, the data collection did not change. We are still using, I think, statsd from the instances, and we actually still, I think the proxy that collects everything from all the instances is still named after the vendor. So we haven't changed anything.
Cool. Any other questions? Yeah, here we go.
Did you implement any kind of governance or life cycles around the alerts to make sure that alerts did the same if they weren't actually needed anymore?
Governance around the alerts?
Not that I'm aware of. I think, I mean, if vendor services are deprecated or something, then we do that. But other than that, I don't think we do anything like that.
I thought I saw one on top. Yep.
Can you comment a little bit about alert fatigue? If you're talking about 100,000 alerts per minute, and just the boss is saying it's all alerts.
Yeah, commenting on alert fatigue.
On the on-call rotation?
Yeah,
I
boss
think-
on the on-call
okay,
rotation, I like
maybe I think I messed this whole thing up, if that's the question. So 100,000 alerts is not actually firing alerts. 100,000 alerts is how many alerts there are that could fire.
Gotcha. All right. Any other questions? I'm sure we've got everyone here. All right. Let's give another round of applause.
Thank you.
All right. So we are pretty much on schedule, maybe a couple of minutes early, which means you can go get yourself another donut. We will see you all back here at 11 o'clock. back, everyone. Hopefully you got some coffee with that donut. I'm not gonna ask, are we up? I'm gonna ask, are we up to 5? 5? Are you, now here's an ultimate question that I am dying to know. Are you having 5 of the same, or you want to try one of all?
Mixing it up. Some of you forget the
Okay. I know, I'm like, I want another apple fritter, but it weighs multiple pounds. And just the thought of that scares me, so. Anyway, we're gonna kick off this session with speakers, some sponsors, one more speaker before we head to lunch. Like I said, coffee's in the back, definitely get some of that at the next break. Lunch channel as well for all of the great lunch options. And yeah, with that being said, let's give a big round of applause for our next speaker, Joe.
All right, well, thank you for that introduction, and thank you all for coming to the talk. So my name is Joe Ross. I work at Splunk. Fortunately, I think some of the previous talks here have sort of hinted at the general topics of quantile estimation and service level things that are sort of a consequence of that. So that's a little bit fortunate. Somewhat less fortunate is that before yesterday afternoon session, I had already put this parade of logos slide, so I'm a little bit bashful about trying to follow that act. But anyway, I used to work in pure mathematics. I spent some time at Signal Effects, and for the last pandemic or so, I've been working at Splunk. And now we have to stare at this for a few seconds. Okay, moving right along. Okay, so I'd like to sort of formulate the core mathematical or statistical problem that I'll be focusing on. So it's given a stream of numbers, x1, x2, and so on, to build a data structure that can answer rank queries, and where the rank of some number is simply the number of stream elements that are less than or equal to that number. A related quantity is the quantile of the stream. So here q is the number between 0 and 1, and this just asks for some number whose rank is exactly that number q times the stream length. Right? So if q is equal to 0.5, then we're just talking about the median. So there are some requirements you might ask for this data structure to satisfy. So one is that it should operate online, meaning that it processes the stream exactly once. Another thing you might ask for is that the size of the data structure should have a mild dependence on the stream length, which, by the way, is not known or bounded in advance. So we certainly don't want to store the whole stream. Ideally, we have logarithmic, or maybe even something smaller than that, dependence on the stream length. And of course, we also want the update operation, which says, I have a data structure, a new point has arrived, I'd like to incorporate that, the sort of add operation, and also the rank and quantile query operations should be fast. So the sort of routine application is to service level, objective, and agreement, so on monitoring. And I think we've seen this on a bunch of slides, but for example, over the last month, I would like to know if I've served some very high proportion of requests within some agreed upon threshold. Right? And you can also imagine sort of turning this into an anomaly detection problem where you compare maybe the last day to the last month or the preceding month. And if you think about metrics other than latency measurements, you could sort of see this as a foundational building block of an anomaly detection system in general. So sort of using these quantiles over time to form baselines for metrics. Okay, so the first results in this general field basically say that if you want to answer quantile queries exactly, and you want to have mild dependence on n, then you're out of luck. So Munro and Patterson proved that for an algorithm that passes over the data p times, if you want to answer rank and quantile queries exactly, you'll need at least the pth root of the stream length size in order to do this. And so in particular, if you want to answer queries exactly in the online setting, which is where p is equal to 1, you'll need to store the whole stream, or a data structure of at least that size. And it's actually a kind of nice so-called white box argument. So you imagine that you have a buffer of some size, so say size S. You're kind of sweeping through the stream. A new point arrives, say the buffer is full, a new point arrives, somebody is going to get kicked out because you only have size S. Now you just arrange that the next element that arrives in the stream, in terms of the items that you still have, has the same rank as the one you just kicked out. Okay? So in terms of the information that you actually have at that point, you have no way of comparing the thing that just arrived and the thing you just kicked out. And so somewhere in the quantile space, you'll have a problem of at least size n divided by s. Right? And so if you keep doing this, what you see is that you'll need at least the pth root of the stream length if you want to answer rank or quantile queries exactly. Okay? And this sort of leads us to formulate an approximate version. So if you want this requirement of mild dependence on n, then you'll also have to ask for some, you'll have to allow for some relaxation. And so you might say that I don't need to return the rank or quantile exactly, but I'd like to do it within some bounded error. So give me an approximate rank, rank hat, that differs from the actual rank by some error epsilon. Right? So if epsilon is 0.01, then I'd like to, my answer for the 95th percentile should be somewhere between the 94th and the 96th percentile. Okay, I'll just make a few comments about what this condition actually means. I think there may be some confusions about this. So maybe the most important thing is that the error condition is formulated in quantile space, not value space. In other words, the estimate has to be between, of the 95th percentile, has to be between the actual 94th and 96th. We are not requiring that the estimated 95th percentile is within 1%, like 1% in milliseconds, for example, of the true 95th percentile. And this may seem a little bit odd, and if you think it's odd, I probably won't convince you that it's not odd with 4 bullet points, but anyway, I'll just kind of say them, and maybe you'll feel differently when you wake up tomorrow. So one is that this is a formulation that makes sense for streams drawn from arbitrary ordered sets. So we generally think about numbers, but actually these data structures would also work for strings, for example, lexicographically ordered. This formulation also has the nice property that is invariant under monotonic transformations, right? So if somebody is seeing some stream x1, x2, and so on, and somebody else is seeing a stream, 100 plus x1, 100 plus x2, and so on, the sort of answers that they'll give if you subtract 100 from the person who's seeing that translated stream will be the same. Whereas if you use a data structure that has guarantees in value space, the answers that they give and the qualitative statements that they can make are actually rather different. So it's a little bit awkward. It's also the case that the problem for guarantees in value space has several simple solutions. So basically, if you're interested in relative error bounds in value space, you can just use logarithmic histograms, right? It's not really that much controversy. Like we don't need to write any papers about this. It's fairly straightforward. And then perhaps most amusing, guarantees in quantile space can be arbitrarily bad in value space and vice versa, right? So these are sort of just different problems, right? So if you have some histogram and all of the values are sitting in a single bucket, you can't actually say, and you don't actually have any guarantees in quantile space. Right? And similarly for these data structures, in general, you don't have any guarantees in value space. Although in practice, you can kind of see some correlations, although this is very data dependent. Okay, so another aspect that we like to have is that the data structure is mergeable, and that means that if we make one of these D1 on a stream X1 and D2 on a stream X2, then we can define a new data structure, the merge of D1 and D2, which has similar error guarantees to those of D1 and D2. So it doesn't have to be the same as making the data structure on the union, but in terms of the error guarantees, it should be very hard to distinguish those two. Right? In terms of quantiles, if you sort of operate on the bottom row of this diagram, if you know the quantile of some set x1 and another one x2, you know that the quantile of the union lies between these, but otherwise you can't really make any guarantees. Whereas if you operate in this sort of richer space of these data structures, which we'll get into shortly, you can merge these two and still extract the quantile with some guarantees. Okay, I'll just pause for 5 seconds to see if there are any questions at this point. Okay, yeah. So, I give a bunch of talks at virtual conferences, and there are the problems that you're sort of talking into your monitor, and you have no idea whether or not the audience is is following. And so now I actually have the same experience of not knowing whether or not the audience is following when I'm up on a stage. So just sort of forgetting the requirement that we operate online. Imagine, just as a sort of thought experiment, that you could store the whole stream, right? So someone's going to say, I'm going to throw a bunch of numbers at you, and then you don't have to operate online, you can store everything, but after that, I would like you to make a very compact read-only data structure that can answer rank and quantile queries, right? And let's say I tell you epsilon is 0.01, right? So what you would do is, let's say I give you 7,000 elements, you store them, you sort them, right? And then you would take every 70th element, right? And that would guarantee that if I give you some element, you just find its neighbors, if you want to, and then you count how many are to the left and to the right. That'll tell you the rank. And if you want to know a quantile, you just sort of travel along this list of sorted elements. And so generally speaking, all of the data structures that we'll discuss are trying to do this sort of sampling across quantile space evenly. The problem is that you're not actually able to store the whole stream. And so when you keep an element, you have to have some concept of its rank, or how many elements are to its left and to its right. And this is sort of the fundamental problem that all these data structures are trying to solve. So how do we achieve this when we're not actually able to store the whole stream? Okay, so the first data structure in this direction was invented by Greenwald and Khanna, and it maintains a set of triples. So V is some element that's sampled from the stream. There's a quantity G, which is the difference between some bound on the rank of that element, the difference between that and a bound on the rank of the preceding element that you've stored, and another auxiliary quantity called delta, which is basically a difference between an upper bound and a lower bound on the rank of that element. And so if you think about it, you really just want to store the difference between, you just want to store, you want to basically get a sense of how many elements could be to the left or to the right, and it just turns out to make the mechanics work, it's a little bit easier to store these auxiliary quantities rather than Rmin and Rmax themselves. Right, and so if you ask what the error is, it turns out that it's bounded by the largest over the elements that you've kept, 1/2 the sum of gi and delta I. You can sort of work this out with some simple algebra. You'd like to be able to insert things, so if you have a new element, you insert the triple v1 and then the floor of twice epsilon times the stream length. And so you'll get a bunch of elements. You'll have a bunch of v's, ones, twice epsilon times something, and then eventually you'll have too many things. So periodically you sweep over this collection and you try to merge triples in such a way that the sum of g and delta is basically twice epsilon, which is your error target, times the stream length, right? And so when you do this merging, the g's add. And the delta is basically the sum of g plus delta, right? So there's a little bit of interaction between those terms. And it turns out that this data structure can answer rank queries with the prescribed error epsilon, right? So you don't have to specify any bins. You just say, this is the error I want. You'll get a data structure that can do this, and it requires the space listed here. The unfortunate thing is that this structure is not known to be mergeable, and it's suspected that it cannot be merged. Okay, so there's a sort of variation on that, which is called the KLL sketch. And this is, again, a sampling device that's very careful and hierarchical. So the core structure inside the KLL sketch is called a compactor. And this is basically a collection of k items in order. And they each have some weight w, which represents how many elements they're standing for. Okay, so it's just a bunch of elements with some weights. And what you can do to this thing is, well, you can compact it, and that means you can produce something which has half as many elements with twice the weight. Okay, and when you actually do this, you keep the even or the odd elements with equal probability. Okay, so here's a picture. So I have this compactor. It's got the elements A through F. They each have some weight W, and someone says, hey, compact yourself. And I say, okay, well, now I'm B, D, and F, each with weight 2W. Okay, and so all we're going to do is basically arrange a bunch of these in some hierarchy. So a bunch of stream elements are going to arrive. We're going to keep them in sorted order. So we have k of them. The next one arrives, and we ran out of space in this level. So what do? Well, we perform a compaction. So now all of a sudden we have half as many elements, and we have to pass them up to the next level. So at that point, we have this next buffer, or this next compactor, is a little bit less than half full, and we've got a single element sitting in level 1. Right, some more elements will arrive, the compactor in that level 1 will again fill up, we'll perform a compaction, pass all of them to the next level. Eventually level 2 will fill up, and so on, right? And so we'll eventually have to make some large number of levels. But this is sort of the core idea, and then, I mean, the description is not that hard. What is maybe a little bit more difficult is actually analyzing the error in this data structure, which you can do using Höffding's lemma. And then there are a bunch of optimizations that these authors came up with. You can sort of replace the low weight compactors with sampling, right? And then you have to treat the heavier compactors with a little bit more care. But eventually, if you use some randomization, you can get this data structure down to the optimal size, which is the order 1 over epsilon. And this has the nice property that it's mergeable, right? To do that, you just concatenate in each level and then perform a sorting. Okay, so that's very nice. Any questions about this? Okay, so again, it's sort of like motivated by the Greenwald kind of thing, but it's a little bit simpler conceptually, and the sort of statistical analysis that studies its error is actually just a few pages. So it's really a nice conceptual advance. Okay, and so we often care about latency distributions. And here, you might care a lot about the difference between the 95th and the 96th, or even the 99th and the 99.5th percentile. But you really don't care that much about, say, the difference between the 50th and the 51st percentile. Right? And so if you're interested in the tails of a distribution, which I think in many operational scenarios is the case, you might want a different concept of error that this data structure should try to meet. And so this is formulated as relative error. And basically it says, so one way to think about it is you have a bound on not the difference between the estimated and the true rank, but rather the ratio of the estimated and the true rank. Or you can say that this difference is bounded by epsilon times the smaller of the rank and the stream length minus the rank, depending on whether you're near the minimum or you're near the maximum. And of course, this is a strictly harder problem than the original epsilon approximate condition that we had, right? Because the rank and n minus the rank are obviously smaller than the stream length n, right? And so it will turn out that solving this problem provably requires more space. Okay, and so one data structure that really tries to bring this concept of relative error and even generalizations to the forefront is the T-digest of Dunning and Ertl. And so the basic idea is that we maintain a sorted list of centroids, CW, which represents W points near some number C. And there's one variant where you're basically performing incremental clustering. So you have this collection of centroids, a new point arrives, you find this closest centroid. If it has space, you add it. If it doesn't have space, you form a new one, right? And then there's a merging variant, which uses arrays, has a sort of buffer of things that you need to incorporate. And this one actually avoids dynamic allocations in the implementation of Dunning's T-digest library, although it does have some slight accuracy issues on some streams. And the thing that sort of makes this go is the concept of a scale function. And this is basically a function from quantile space to the extended real line, which says how accurate do I have to be as a function of where I am in quantile space. Okay? And there's also a compression parameter called delta, which basically controls the number of centroids that this data structure will have. So it controls the size. And the condition is that if you have a cluster or a centroid that occupies some region in quantile space, say Q1 to Q2, then when you apply the scale function k and look at the difference between the endpoints, that difference can be at most 1 over delta, right? Or the cluster can consist of a single point. So in the case where you have a linear scale function, then you're basically asking for the cluster size to be constant in Q, and that corresponds to the original epsilon approximate condition, where you ask for 1% error in quantile space everywhere in the distribution. But it gets a little bit more interesting when you start writing down fancier scale functions. So this one is from Dunning's paper, so it's the log of Q over 1 minus Q. And as you can see, it's sort of increasing very rapidly near 0 and 1. And if you look at 1 over the derivative of the scale function, that basically describes the cluster size. So we're allowing for fairly large clusters in the middle of the distribution, where we don't care that much about accuracy in some operational scenarios. But we're asking for relatively small clusters near q equals 0 and q equals 1. So we can expect our answers to be much more accurate in those parts of the distribution. Okay. And so it turns out that the mergeability of a t-digest can actually be translated to an explicit analytical condition on the scale function. Right? So basically you have some little cluster inside quantile space. When you make an insertion or merge with another one, it's going to slide around a little bit. And you have to make sure that when it slides around, all of a sudden the space that it occupies with respect to the y-axis, so to speak, doesn't become too big. Okay? And so you can write down some condition. It's a bunch of inequalities. And then you can actually show, using this condition, that differentiability is required. So if your scale function has any place where it sort of looks like this, which is what it looks like if you zoom in small enough, then you'll be able to realize some insertion or some merging where that requirement on the case size of the cluster will become violated when you sort of move over to the region where the derivative is larger. Okay, and there are many scenarios. So all the original scale functions had a symmetry about the q equals half line, and there are many scenarios where we care very much about the quantiles near q equals 1, but we don't really care about quantiles near q equals 0. Right? And if you sort of look at the explicit condition that you can derive analytically, and also the requirement of differentiability, you're sort of naturally led to a construction which basically says, well, I don't want to use the original left half of the function k2, for example, but I want to keep differentiability. How about I just replace that part of the graph with its tangent line, right, and extend that? And that corresponds to keeping the cluster size relatively large on exactly 1/2 of the distribution. And it turns out this sort of works in the sense that if you make this construction on any of the known scale functions, you preserve the mergeability property. Okay, so this gives you, so roughly speaking, this allows you to reduce the size of a t-digest by 40% and have basically the same accuracy near q is equal to 1. Of course, you have less accuracy near q is equal to 0, but you didn't really care about that, and you maintain the mergeability aspect. Okay, and then there's a sort of a variation of the KLL sketch, which did this compaction thing, where if you think about this cluster size, if you sort of invert that, you can think of that as describing a sampling intensity, right? And so the idea of the relative error quantile sketch is to just make a compactor that doesn't sample uniformly, right? And so this is kind of a cartoon of it, but basically on the left-hand side, there'll be some little chunk of the compactor that always participates in removing half of its elements. And then the next little segment will have half of its elements removed half of the time. And then the next segment will have half of elements removed only a quarter of the time. And then the right half of the distribution will never be involved in a compaction. Okay? And then there's kind of a similar hierarchy. Actually, the definition is not too much more involved, but the analysis is a lot more delicate. It takes like many pages instead of just 1 or 2. And the resulting sketch is quite a bit larger, as you can imagine, since there's basically half of the stream that we're never sampling from. But this is provably needed, which you can maybe guess from the difficulty of the relative error condition. Okay, so I submitted this a couple years ago, and I actually had at Splunk there were some other people who knew about this problem, and I ended up being introduced to some of the people in the KLL circle, and we tried to do a comparison of the rec sketch and the t-digest. And we basically yielded some of the theoretical arguments for the rec sketch against some very detailed knowledge of how the t-digest works internally to come up with some adversarial examples for the t-digest. So I don't know, I love this stuff. So let me try to explain how the t-digest might make errors for you. Okay, so they're basically 2 sources of errors, and we're going to combine them. Okay, so as I sort of mentioned, in this t-digest scenario, we have a bunch of elements. Periodically, we sweep over them and take the average of a bunch of points, sort of weighted average, and use that as the centroid representing that collection of data. Okay, so there's one situation which is not so great for this, which is if you happen to have a centroid that represents a single point x1 and then many copies of the same point x2, which is equal to x3, so on, then if you ask for the rank of some element between c1 and x2, you only have C1, right? You threw away the x's. You think this point is bigger than C1, but it's actually less than almost all of the points that are represented by C1. So that's not great. Okay, so the mean can be very different from the median in a single centroid. And the other problem is that since you only have the centroids, and those are ordered, so those are ordered, but they're only weakly ordered. So you know how the centroids compare, but you don't understand how the data sets that contributed to those centroids actually compare. So in the top line, we have the same lopsided centroid from the previous slide. Now imagine you sort of, you got this knife in there, you're just twisting it, right? So you find this place where there's a bunch of error. What do? You do the same thing over again, right? So you make another lopsided insertion. Now I'm calling them Y1, and then a bunch of copies of a point Y2, right? So again, you have another lopsided centroid. So now imagine someone asks you we asked this digest for the rank of some element between C2 and Y2. Okay, so as far as the digest is concerned, we only have the red stuff, right? So we think it's bigger than C1 and bigger than C2, but if we had the whole stream, we would realize that actually this point is less than almost everything that contributed to those centroids, right? So it's less than Y2 and it's less than X2. And so, this is kind of the idea. It takes a lot of, it takes some work to actually make this precise, but the sort of punchline is that you can realize this attack on most of the implementations of tdigest, and just having more centroids or increasing delta doesn't really help you. There's also a formulation where you can just write down a distribution that uses kind of mixed scales. Okay, do I have a minute left? Okay. All right. Any questions about this? Okay. Okay, and then the last approach I want to mention is a bit different. So this is not really trying to do any sampling. It's more, I say, classically statistically based. It's called the moment-based quantile sketch. And so just as maybe it's called a straw man. Just imagine we're a little bit lazy. We have some package that will compute for us the rolling mean and the rolling variance or standard deviation. Well, one thing we might do is just say, maybe my data is normally distributed, which could be the case. I mean, it's definitely not, but it could be the case. And then use its quantiles, right? Use the quantiles of the normal distribution to estimate the quantile of the actual stream, right? Or to answer rank queries. Okay, well, I think we can all come up with counterexamples to this. I mean, it sort of shows up on any slide involving latency distributions, right? So here's a pair of distributions which have the same mean and the same standard deviation, right? Of course, they're quite different. And if you just use quantiles of one, you will not accurately estimate quantiles of the other. Okay, but I know how to tell these apart, right? But this is not me, this is somebody else, but I know how to tell these apart. I know that the one on the left, which maybe looks more like a latency distribution, is skewed, right? The one on the right has no skew, right? And the skew is, I mean, just as the variance you could think of as the average of the squared distance to the mean. The skew is basically the average of the cubed distance to the mean, okay? You're supposed to divide it by something, but morally this is what it is. And so if you analyze this quantity on the left, you'll get something positive, and if you analyze this quantity on the right, you'll get 0, okay? So then the question becomes, well, if I know the mean and standard deviation, I can write down the normal distribution. If I know the mean and the standard deviation or the variance and the skew and the kurtosis and then the next of these sort of centered normalized moments, however they're called, how do I write down a distribution so that I can use its quantiles to estimate the quantiles of the stream? Okay? And one way to think about this is, well, if I have this pair mu and sigma, how do I characterize the operation of taking the normal distribution? Well, one way to describe it is that you are picking the distribution with the largest entropy, realizing those two moments, right? Among all distributions with a fixed mean and standard deviation, the normal distribution, in a sense, is the least informative, right? So it has the highest entropy. And so this is the sort of thing that generalizes well to this scenario where you have multiple center normalized moments, right? So you ask for the distribution which has the largest entropy, subject to the constraint that it realizes a certain collection of statistical moments. And it turns out the solution to this can be drawn from an exponential family, which has a very efficient numerical solution. And in terms of observability, maybe the interesting thing is that the merge operation can be vectorized, right? So you don't actually store the mean and the standard deviation. You have to do something a little bit fancier. Like conceptually, you're keeping the count and the sum of squares and so on, but you do it in a numerically stable way. But the merge operation can be expressed in terms of first adding a bunch of vectors together and then doing a little bit of math and then solving this problem and then finding this distribution from the exponential family. So if you ask for some quantiles over a very large number of combinations of some attributes and possibly over time, and you have to do millions of merges, this is something you can actually do efficiently. And there's I think it's called a plugin or an operator for Druid that implements this moment-based quantile sketch. Whereas if you use something like the KLL sketch or the T-digest or any of those variants, when you do a merge operation, you're basically merging two sorted lists. And this is something that you usually can't do very efficiently if you have millions of such lists. So for some scenarios, this approach, while it doesn't have theoretical guarantees, has some very attractive qualities. And that's it.
Awesome. Well, whenever people sometimes conference talks at monitoring events are they're too high level, they're too forward thinking, I will always point them to Joe's talk, which always makes me think, I was told there'd be no math. Anyway, we do have time for any questions from the audience. Yeah, got one right here.
So, do you have an opinion on what observability systems, which of these techniques we should use, and how much would it cost us to implement something good for latency, for example? If we want the 99.99th percentile, how much storage would it need?
So what the techniques would be and the cost.
Yeah, no, that's a great question. So in terms of the cost, I don't think I can say anything definitive right now. In terms of the maturity of these various data structures, the KLL sketch it has an implementation in the Data Sketches Apache project, which I believe has been pretty well tested. The rec sketch, I think, would be more suitable for observability use cases where you care about these quantiles near q equals 1. So I haven't actually looked into this in the last few months, but I believe that hasn't been quite as battle tested. It's sort of based on the same code base, but I presume there are a lot of edge cases that we maybe haven't really analyzed in the wild. So I would hope that eventually, if cost permits, that we could use something like the rec sketch, relative error quantile sketch. There's this kind of thing that's waiting for you, which is if you want the data structure to have a fixed size, which I think everybody wants, you cannot actually have any guarantees on the error, right? So like the KLL sketch and the rec sketch require, there's always some logarithmic factor, right? That's kind of just waiting for you as an inherent difficulty in the problem, right?
All right. Is there another question out there? Up top? I just want to call out too that it's always fascinating to see in different slide presentation systems. This is all in a Jupyter notebook, right?
Yeah, Jupyter notebook slides.
Which is just, again, incredible stuff. So great. Thank you again. Big round of applause for Joe. All right, so we've got this section of sponsors to share with you more of their great products. Again, out in the sponsor space, please spend some time during the breaks to check out, collect some swag, some socks, and chat with them about their stuff. First up is going to be Honeycomb.
Hello. Are you things working? We're almost there. Presenter view, come on.
Oh, that's good. That's good.
Yeah, we got
To,
it.
to that very kind Google engineer that reached out to me, I will email you my feelings. There's one improvement that will make this so much better. Only one.
Yeah. Don't spin up as a separate tab. Exactly. New window. New window. Oh my goodness. And of course I hit the wrong button. I will get better at this, I promise, next time. All right, sorry about that. We're going to talk about this one word today. I'm not going to actually show you any product. If you want to see a Honeycomb product, come see us at the booth. We'll be happy to demo the product for you. Instead, I'm going to talk about observability, because this is a word that means a lot to us at Honeycomb, because we kind of coined it a long time ago, and now everybody else is using it. And I'm not sure they're using it the right way. I'm not sure they're doing what observability really is supposed to be. Observability, when we coined it, when we brought it into this world, when we said, hey, let's use observability in software, we use it from the engineering control theory as a measure of the internal state of your system from its external outputs. And this is what we mean by that. We mean by being able to understand what's going on inside of your system by looking at its outputs. And this is great. People are like, awesome, observability's everywhere, and everybody's going talking about it, and I'm going to do observability product vendor A and B and C and everything else. Fine. I'm going to tell you what observability is not, okay? The 3 pillars of observability, right? What are the 3 pillars of observability? Logs, traces, and metrics. Is that it? I got it right? 3 pillars of observability are really berry, strawberry, banana, and mango. There are no 3 pillars of observability, okay? That's not what observability is. Because you do logs, traces, and metrics does not mean you are an observability company. You're not doing observability better, okay? Here comes rum. Here comes synthetics. Is that going to be my 4th and 5th pillar? I feel like we're getting into the Mach 3 razor blade wars, right? Mach 3, then here comes a shit 4-blader, and then we're going to do the Mach 5. You skip all that crap. Let's just go to Mach 15 right now. Because that's where we need to be going. Okay? Like, it is not 3 pillars. It is not different kinds of data. It's what you do with that data that makes observability. It's not another word for monitoring. It's being able to get fast answers from any questions, even questions you haven't thought of yet. That's what observability is. Being able to answer questions about things that happened this morning, that you deployed this afternoon, that you just didn't know could do breaking in a different way. So when did this all come about? When did Honeycomb really start talking about observability? We had to do some digging. We had to dig and keep on digging. And I found the tweet. It wasn't even us that tweeted it. It was somebody else. And although Charity Majors, or also known as Mipsy Tipsy, and if you've not followed Mipsy Tipsy on Twitter, please polish that rock that you live under and throw it away and follow Mipsy Tipsy on Twitter. She's got great hot takes all the time. Lately she's been ranting about CD not being real. Follow her there. But we came out, this is January 5th, 2016. There was also a talk at Monitorama 2016 in June that year. And then 2017, there was another talk about observability. And then here we are, 2022, because we had a small hiatus and everybody's doing it. We have been doing it from the ground up. This is how we built our product to do it. Observability is such a thing, we wrote the fucking book on it. You can come get the book. We have a few more left at the booth. Come get your book. And if you already have a book, we also have cool sticker sheets that you can add stickers on the Fox, make this Fox all pretty and unique and yours. It's really fun. You should get the stickers. Observability is such a thing now. I know a couple people, most people here don't care about the Gartner Magic Quadrant, and I get it, right? You're not that kind of business, you're not into it. But I've seen some JP Morgan people here, I've seen some other, perhaps larger enterprises. You care about the Magic Quadrant. Well, this year, Gartner renamed it. They added the word observability to it because it matters, because it's a thing that we care about, because it's catching on. But you know what observability is? Observability is being able to answer this. If you can't answer this kind of question today, then you are not doing observability. And the question we're talking about is 0.3% of my users are having a problem because they're Canadian like me. They're using the French language pack on an Android phone, and I'm the only one of 4 other people who are having the same problem. That's observability, is being able to find the real diamonds, the real needles in that haystack. And I'm going to kind of close out here with one small rant I have. Because they fucking suck. They do. Dashboards are a view into a previous time. They are a collection of things that have gone wrong before, and you're going to throw them on a dashboard. Because if it goes wrong again, you could catch it. Great. What about the code you wrote this morning and you deployed to production this afternoon? Where's a chart for that? Dashboards don't exhibit great behavior. And what we want you to do is think about not using dashboards, but think about exploring your data and asking questions of your data. If you're going to leave this conference with the notion of, I'm going to bring an observability culture to my company, you owe it to yourself to call Honeycomb the people who coined and who started this whole entire observability movement from the get-go. Understand how it is that we approach the problem differently using exploratory tools instead of relying on a sea of endless dashboards. Because really, we don't pay SREs to watch TV. We pay you to help fix things. My name is Pierre Tessier. I work for Honeycomb. That's my talk.
Awesome. Yeah, I remember that year he was talking about for observability. It was I think Roy Rappaport. He had given a talk where he talked about a Netflix observability team. It was like such a shift in words, right? Because everyone had a monitoring team, no one had thought of an observability team before, in very much the same kind of fashion. So, all right. All right, let's give a big round of applause for, nope, not yet, no applause. These are the worst. All right, yeah, want to do it? All right, big round of applause for PagerDuty.
Yeah, thanks everybody. Sure appreciate the time here and appreciate your investment on behalf of yourselves and your teams in Monitorama 2022. It's great to see everybody here again. Just wanted to share a little bit about PagerDuty. The company was founded a little over 12 years ago to really solve some of the problems and the toil with a manual on-call process. Today, PagerDuty is represented at over 15,000 different customers globally. We've got over 1 million users on the platform. And we're really helping bring together, kind of the manual, automated, and machine learning processes to help in those areas. So we'll kind of jump right in. The past couple of years has really seen all of us in our organizations and the world really shifting to digitized operations. And that's where PagerDuty can really help out as we're, focusing on these customer-centric systems and applications and engaging with our internal and external customers. And really, bottom line, the overall move is to automation. And so what, sort of problems or challenges does that pose for us? Well, of course, the volume of data is growing. Systems are getting more complex, right? And it's the ability and stretching the limits of teams to deal with that complexity. So in the more manual or traditional worlds, at worst case, we're running at kind of ticket speed, or we've got some things in the queue, and at best case, we've got manual teams and folks that are helping accelerate or move those things along. But in today's world that's moving and really accelerating into digitized operations, what we really need is that machine speed to help with automation. And that's where PagerDuty can help out. So think of any sort of unplanned critical work, right, for your organization, regardless of what it is, that really can't wait in a queue, right? It's when seconds matter, minutes matter in terms of serving your customers, keeping systems up, availability, and so getting to that resolution for whatever issue or error or customer problem that comes up is really critical, and that's where we can help shorten that time as you get into a mature digital operation space. You really want to get to that resolution as quick as possible and get folks back to their main jobs, right, which is kind of building the future for your customers. So this is an example of kind of some of that complexity I was talking about. Specifically, this is a services dependency map for Netflix, and it's made up of, as you can see, thousands of microservices and interconnections there. But behind every one of those, blue dots and lines around the edges there are a set of teams, right, a collection of people. Built particular codes, they've got multiple dependencies and integrations, and so when something disconnects or breaks, how do you get to that resolution and understanding what's upstream, what's downstream, what's impacted? There's a lot of complexity here and a lot to deal with. So this is where you can really leverage that automation and machine learning to help with that response. So PagerDuty, we're really trying to revolutionize the operations space, building customer trust, and really helping you anticipate, anything in an unpredictable world. So that's really the goal of PagerDuty, is to help you as teams work together and accelerate that machine automation. So what do we see this looking like for a majority of our organizations, and probably what you see in yours too? It's really starting to center around your customers. Again, whether those are internal or external, that's all kind of where the start of the process is and where you're trying to serve. So on the right-hand side, we kind of think of these 4 different pillars of things that we're trying to accomplish. Automating everything, connecting everyone, connecting everything, so no systems are an island or left alone, and then really giving you the flexibility, right, in terms of working with various teams or global organizations. So what does PagerDuty do in a nutshell? Kind of looking left to right here, we'll ingest a lot of signals from across the board. It might be from systems, applications, infrastructure, and we really bring together kind of that human portion along with the automation and event management and intelligence to help all the teams within your organization keep things available, keep things running smooth, and focusing on building and innovating for the future for your customers. So a little quote from one of our alliance partners, Andy Jassy with Amazon, again, comes back to that point around availability, right? If you don't have availability, you really don't have that customer experience. So that's what you're wanting, that's what you want to maintain, that's what we're all here for. So PagerDuty really helps with kind of that quick time to value, right? Because again, when you're talking about seconds matter, you really don't have a lot of time to build up and get this going in your environment. So we really work with our customers in terms of driving that payback or time to ROI and implementing the systems, and again, kind of automating everything and building that function around there. Lastly, as I mentioned in my opening remarks, we've got about 15,000 customers globally, million users on the platform. What that gives us is this history of 12, 13 plus years of data that we feed into our AI and machine learning tools and capabilities as well. Again, bringing the humans together with the automation and the incident response to help you get to the resolution quicker. So I think that's it. Thank you so much. Safe travels to everyone, and thanks for coming.
All right, thank you. And last but not least, we have Elastic. It's gonna work. It's gonna work first time. I knew it wasn't gonna happen. Google Sheets.
Hey.
All right, here we go.
All right. Hi, I'm Nathan Smith. I work at Elastic. I'm the team lead for the infrastructure monitoring UI team. And today I wanted to talk to you about some work we've been doing. I'm a member of what's called the Platform Observability Working Group, which is an internal group where we're trying to solve some problems that arise from having to maintain monitoring systems and making that easier, and we can also apply these learnings to help you using our products. So this is Elastic Stack Monitoring. This has been around a long time. It predates what we call the Elastic Observability products. It was built a long time ago, and I'm going to kind of show how it works here. In these examples, I'm talking about Kibana. This can also apply the same ideas would apply to monitoring Elasticsearch or Logstash or anything. That's what we call the Elastic Stack components. So here we're talking about Kibana. And if I want to collect metrics from Kibana, Kibana exposes an API endpoint that I get stats out of. And then I can collect those with MetricBeat. We collect logs with FileBeat. And then MetricBeat has a Kibana module. And then that gets sent to a monitoring cluster where the stack monitoring UI can show you dashboards and information about your cluster. This is very expensive to maintain, and my team has the responsibility of maintaining it, and we'd like to eliminate some of that maintenance cost. So if you see here, if we want to change something in this, if we want to change something here, it has to be, we have to change the API endpoint, we have to change the metric beat module, and we have to change the UI if we want to add a new chart. So that's very time consuming and not very cost effective. So our proposal as the Platform Observability Working Group is this. Instead of having this custom API endpoint, we're going to expose a Prometheus endpoint. And instead of the Kibana metric beat modules, we're going to use the existing Prometheus integration for Elastic Agent. So everything we're doing is all features that already exist in Elastic. So we're not building a Prometheus integration that already exists. We're using the OpenTelemetry metrics SDKs to instrument metrics in Kibana. And so when we do that, we can use those same APIs in Elasticsearch or Logstash or anywhere. And then, so since we're already doing this, pulling metrics with Prometheus, and we're already using the SDKs of OpenTelemetry, we can use OTLP. If we want to push those metrics to the Elastic APM agent. The APM agent already supports receiving OTLP, so we just need to send it OTLP. We don't need to build anything. We don't need to customize anything. We just need to send data to our existing integrations. This makes it a lot easier for us to just use OpenTelemetry. So we're just going around telling teams to use OpenTelemetry to instrument their systems. And since we're doing this, we're sending OTLP to the Elastic OTLP receiver. If anybody else wants to monitor Kibana, we can just send this data to any OpenTelemetry collector and do anything with it. And this will allow us to really focus on the user experience and not maintaining a lot of legacy systems. So using OpenTelemetry and instrumenting everything in Elastic with OpenTelemetry will make it a lot easier for us. And if anybody else needs to needs to consume data from Kibana or any of the Elastic Stack components, you can just send it to an OpenTelemetry collector. And so we really want to focus on the best user experience for monitoring, the best observability product, and not really wanting to maintain Elastic Stack monitoring. So OpenTelemetry is enabling us to do this, and hopefully it can be helpful to you when you're instrumenting your applications and using Elastic Observability. So thanks, Monitorama. It's been an honor to be here, and enjoy the rest of the conference. Thanks.
Alrighty, while our next speaker is getting set up, I appreciate the kind of crowdsourcing around the company Grok that we talked about yesterday in our talk. And I can't remember who it was, I apologize, put a great note into the general channel that the founders of Grok were actually the creators of the Palm pilot, which is, I don't know how many people had a Palm Pilot or just remember those, right? Like, I was mind blown by that. And also thank you to finding the actual website, which was, I don't know, personally kind of a comical read for me. All right, big round of applause for our next speaker, Oleg.
Hi everyone, my name is Oleg Zaitsev. I'm a software engineer from Grafana Labs Mimir Squad, and today I want to share you some of the challenges we have to overcome in order to handle 1 billion of active series at Grafana Mimir. Last year, we had a business case to run Grafana Mimir with 1 billion active series within a single tenant. Since then, we have made substantial improvements to Grafana Mimir, so this talk is only some subset of the features we have. Before we start, I want to introduce you to Grafana Mimir. Mimir is an open source distributed time series database for Prometheus. It provides high availability, horizontal scalability, real multi-tenancy, durable storage, and fast query performance. We also ship Mimir with rich set of production-grade Grafana dashboards, Prometheus alerts, and runbooks. You can use them to monitor your Mimir installation from day zero, just like we do at Grafana Cloud. Mimir doesn't replace Prometheus, but instead it just extends it. When using Mimir, you keep running Prometheus configured to scrape metrics from your applications and infrastructure, and remote write these metrics to Grafana Mimir. Alternatively, you can use Grafana Agent or Prometheus Agent to send data directly. Then you just configure Grafana to query metrics from Mimir, leveraging on Mimir scalability and performance optimizations. I also want to give you a quick overview of Mimir's architecture to make understanding of the presented challenges easier. On the right path, Prometheus, or Grafana Agent, writes metrics to the distributor, which is responsible for sharding and replicating metrics across the ingesters. The ingesters keep the most recent metrics data points in memory and local disk, and periodically upload these metrics to the object storage. On the read path, Grafana sends query requests to query frontend, which is responsible for accelerating the query execution. I will cover the query acceleration techniques more in details later on. Queries are executed by a pool of queryers, which fetch the most recent data from ingesters and older data from the store gateways. The store gateway is responsible for fetching the actual data from the object storage, and it provides an abstraction layer for different storage providers like GCS or S3. The compactor is a component which asynchronously deduplicates and compacts blocks periodically uploaded by the ingester to the object storage. I will also cover the compact more in details later on. When alerting rule fires, the event is sent to the alert manager, which is responsible for delivering notification through the configured receivers like by email, Slack, PagerDuty, Grafana call, and many more. Mimir's alert manager is based on Prometheus alert manager, and it adds multi-tenancy on top of it. So back to the original topic. What's a billion active series? A series is a set of samples observed at certain timestamps. Each series is identified by a set of labels. In this example, we have two series of metrics named foo with different label values, and we also have a single series of metrics named ba. These three series are active series, since they had samples in the last 20 minutes. The orange series on the left doesn't have any samples in the last 20 minutes, so it's not considered an active series. So today we are talking about ingesting 1 billion active series that received at least one sample in the last 20 minutes. And by the way, I'm talking about it in terms of US billions. I'm saying that because Spanish billion is a million of millions, just like the British one was until not so long ago. That creates me a lot of confusion when I'm thinking about the scale. My girlfriend told me that I should use GIFs in my presentation, so I just added this slide to use a GIF. And scale. I spent a lot of time trying to find a good example of the scale of this number. And I think that the best way is just to take Prometheus instance itself as an example. In my home lab, it exposes 1,000 metrics. So a billion active series would be like scraping metrics from 1 million Prometheus instances. In order to be able to ingest and query such a big volume of data, we had to tackle multiple challenges, like ingester operation bottlenecks, compactor throughput, block index size limitation, high cardinality queries, TSDB matches performance, slow rollouts, and hash ring performance issues. You can also read about them in the blog post that I'm going to link at the end of the presentation. So just like the architecture interview, let's start with the right path. As I explained before, the ingesters are the stateful components of Mimir in charge of storing metrics in memory and disk. In our experiment, we simulated 20-second scrape interval, which meant that our ingesters were receiving 50 million samples per second. This number has to be multiplied by the 3x replication factor later. Prometheus TSDB that Mimir uses stores samples in a data structure called a chunk. Each chunk holds by default 120 samples each, which is the optimum balance between getting the best compression ratio of the samples without getting too long chunks, because those are more expensive to read later. with 120 samples in each chunk and 20-second scrape interval, a chunk gets full every 40 minutes and has to be flushed to disk. This meant that in our test, every 40 minutes, each one of the 600 ingesters was writing to disk around 7 gigabytes of data within a few seconds interval. Since the chunk writing operation was a blocking Prometheus TSDB operation, it meant that we observed very, very slow requests every 40 minutes. So in order to solve this, we added 2 improvements. First, we introduced a jitter to the chunk size. This would prevent them from being flushed to disk at exactly the same time. The jitter depends on the series hash, and to make sure that every ingester replica chooses the same jitter for the same series. We also added the queue-based approach to the chunk writing. So chunk writing would no longer be blocking for the subsequent writes. As a result, the 99th percentile of the write latencies decreased from 45 to 3 seconds, which was within the objective we set of 10 seconds to ourselves. And after ingesting all that data, Mimir must then compact it at the same rate. The original Grafana Enterprise Metrics compactor could only concurrently compact blocks of different time ranges, which meant that all the ingested data from given time range was compacted by a single thread. In other words, a single thread had to compact 150 million samples per second in order to keep up with the ingestion rate. This caused the compactor to fall behind and compact the data slower than it was ingested, leading to lots of uncompacted blocks in the storage, which in turn decreased the performance of the read path. As we approached the billion active series, it wasn't just about the speed anymore. Prometheus TSDB blocks have a 64 gigabytes index size limitation, which comes from series being addressed with a 32 bytes unsynced integer, and they are aligned to 16 bytes boundaries. Having this many series meant that after a long running compaction, it would fail because the output block can be built. We could have modified the TSDB format we used to address that, but we want to keep being compatible with the original Prometheus TSDB, so we had to go a different way. In order to overcome these limitations, we created a new compactor called the Split and Merge compactor. Let's see how it works. This compactor has a configurable amount of output shards. For this example, we'll use 2 shards just to simplify the diagram. Let's assume we have 4 ingesters producing 1 block each. Note that each ingested series is replicated across 3 different ingesters in this 4. First, we run the split compactor stage. At this stage, the compactor instance takes the portion of all blocks, compacts it, and produces as many blocks as shards were configured. Each shard contains only the series which hash belongs to that shard. Then the merge compactor takes the split blocks for each shard and merges them into a single block. Note that merging 2 blocks with series from a given shard produces a block with the same shard. This way we can parallelize the compaction of a single time frame. And we can make the block smaller by just increasing the number of shards, overcoming the index header size limitations mentioned previously. And we can drastically increase the compaction speed. The block size doesn't decrease linearly with the number of shards, because sharding on series hash ends up putting different series of same metrics into different blocks, having duplication of the label names and values across multiple blocks. Like for instance, the job label or the metric name label name are most likely present in every block, but since the index is just 10% of the block size, we are happy with the results. And these are just some of the optimizations we did on the write path, but we also have to do it on the read path. Prometheus PromQL engine that Mimir uses is single-threaded, which means that the duration of each query depends on the length of the time window and the number of series that there is in the storage. This means that you have to scale Prometheus PromQL engine vertically in terms of memory and CPU core performance. And sometimes the question isn't when it will return results. Sometimes it's just will it return or will it crash instead? You all know Prometheus probably. So in order to make it scale, Mimir splits the time range queries into smaller range queries by default. Caching them where possible. This basically means that once you've queried a 30-day range query, the next query some moments later will only reevaluate the last few minutes of new data, relying on the cached results for the rest of the range. When the results are not cached, the subqueries time range are aligned to the block sizes to improve the resource utilization and are executed concurrently to improve the query speed. When the result is not cached, with a billion of active series in the storage, there is a lot of data to retrieve. So we've implemented series hash-based sharding. We call it just query sharding internally. Each query is split into smaller cardinality queries executed concurrently, and then the results are merged back with using an appropriate function. For the example on the screen, when you run a sum of rate of some metric selector, that can be evaluated separately for each shard of the series, and then we can just sum the results. The number of shards is dynamically calculated up to a given limit to optimize the resource utilization. And you can notice that not all the queries can be sharded entirely, like histogram quantile cannot be sharded because you have to calculate it at once. But they can take advantage from query sharding because the sum inside of the histogram quantile can be sharded. At the moment, 60% of all our customer queries running on Grafana Cloud are sharded, and we are working to support query sharding for more query types. On average, we observe a 10x reduction in execution time for high cardinality and CPU-intensive queries. For example, in the screenshot, the high cardinality query running on the same Mimir cluster with and without query sharding enabled, the execution time was reduced from 40 seconds to 4, which is like a long time staring at an empty dashboard. And it's not only about speed, so it's also about the resources. Even though the sum of all executed work is slightly bigger because now we have to post-aggregate again, this increases negligible compared to the benefits of distributing the load across more smaller subqueries. We are so happy with this load distribution that since Mimir 2.1, we support the recording rules evaluation to use an external query evaluator, and we reuse the sharded query frontend path for it, reducing the number of memory speaks in the rulers. I also want to note how well the different improvements work together. Since both query sharding and split and merge compactor use the same series hashing algorithm, we can shortcut query path because we know beforehand whether a given subquery shard does not have any data in a given block shard. This works both ways when there are more subquery shards or more block shards. Of course, even here, there's a room for optimization. When we have a set of matchers, we can't calculate which series belong to a given shard before retrieving all their labels. Whenever the number of query shards is higher than the number of block shards, which is a quite common situation like you can see on the screenshot, the queries end up asking store gateway for multiple shards of the same series. In practice, this means that we end up having multiple coroutines within the same store gateway calculating which series match that same set of matchers at the same time. In order to reduce the amount of duplicated work, we added a promise-based approach and deduplicating the implied queries for the same matchers. Plus, we cache the results in memcache so we can reuse the results from different instances. We also upstreamed this change to Prometheus with an in-memory based cache because, surprise, people are querying the same metrics all the time, so you can just cache the matchers. In our experience on Grafana Cloud, most of the time, the hit rate of this cache is around 100%. So it's awesome because we do this thousands of times per second. And caching matchers is great, but there's no limit to developers' creativity when it comes to writing queries. So we still have to evaluate matchers from time to time. Prometheus does a good job trying to optimize regular expressions when they represent a trivial set of values. For example, in this regular expression would only look up for 2 label values in storage, because that's much cheaper than checking each one of the existing label values and running the regular expression on top of them. However, as I said, there's no limit to developers' creativity, so sometimes we just try to make the regular expression shorter, and we force Prometheus to run the regular expression on all the label values present in the storage. Turns out we are not so creative when we run the regular expressions, and most of the time we do the same ones. We change the code so it would generate a finite amount of values from a regular expression when it's possible. So in the previous example, we still wouldn't need to scan all the label values. Sometimes it's not possible to generate a finite amount of label values, or like a bounded, decent amount of values. Like in .wildcard general expression, we can just merge any string. Or we still optimize some of them, like looking for a substring or checking some specific features. We were able to save up to 90% of CPU time on these common cases, according to our benchmarks. We haven't spin these improvements to Prometheus yet, but it's definitely in our plans. And it's not all about throughput of the application itself. We also made improvement to how we deploy and operate it. One of the issues we encountered were the really slow rollouts of the ingesters and store gateways. As I mentioned before, ingesters hold recently written series, each ingester holding one of the 3 replicas of a given write. We want to keep redundancy at all times, so when we are rolling a new version, we have to be careful not to take down more than one instance holding one of those 3 copies of the series. Kubernetes doesn't know about the distribution of the series, so what we did in the past was rolling out one ingester replica at a time. Considering a 10 minutes restart as an example, because each ingester has to replay all the write-ahead log, that would mean that we would have rollouts lasting for 100 hours or 4 days, so it doesn't really scale. In order to optimize that, we made the multi-zone rollouts as the default ingester and store gateway deployment option. Even when all the zones are deployed in the same availability zone of your infrastructure provider. Once the ingesters are working in a multi-zone configuration, each zone holds one replica of given series. So now we can roll out an entire zone at the same time without losing redundancy. We leverage on another component we made open source called rollout operator to coordinate those restarts. In practice, we don't restart entire zone at once. We do it in batches of 40 ingesters at a time, which gives us enough balance between speed, confidence, and resource utilization. We don't want to kill the nodes just by restarting 100 ingesters. And hash ring in Mimir. This is the last thing, but not the least. Mimir uses hash rings to share work across multiple components, like the series replication across the ingesters. A hash ring is a data structure shared across the Mimir replicas using a key value storage, and we currently support console, etcd, and member list. Since the operation, so when using console or etcd, the entire hash ring is stored in a single key, and every instance periodically updates it with a timestamp using a compare and swap operation. Since those operations are mutually exclusive, there's a limit on how much you can scale, defined by the performance of your key value storage backend. And we hit that limit with our 1 billion active series test, because we were running 1,500 replicas of different services hitting the same backend. Member list is a gossip protocol that overcomes this limitation, and this is now the recommended way to run Mimir. Instead of performing atomic compare and swear operations that are immediately available on all nodes, member list just shares the changes with some instances being eventually available everywhere. However, when we switched to member list in our test, we found out that 1,500 replicas of all microservice components, each replica was using between 1.5 and 2 cores just to propagate the changes using member list. So we investigated, profiled, benchmarked all the related code, and we came up with a set of changes that drastically reduced the TPU utilization. After weeks of making improvements, we were able to reduce the CPU load for member list operation by like 90%. In the screenshot, you can see one of those improvements being deployed on the distributors and queries. So what's next? We are drafting a release candidate this week that includes backfill API, to upload entire Prometheus blocks, and as well as the out-of-order sample suggestion. We are very excited about the out-of-order sample suggestion. Ooh. It is especially interesting for customers who use Kafka to queue the writes because they arrive in different order. And it will also enable us to properly support graphite and Datadog metric format ingestion, which we should be open sourcing later this year. And we obviously are doing much more, but I want to especially mention the efforts we are doing making it easier to operate Mimir. We are adding lots of documentation, we are improving the Helm charts, and we are adding actionable errors with runbooks, etc. And I didn't want to start with this because it was supposed to be a serious talk, but I'm pretty sure that many of you have been thinking about the Mimir, like there's a Mimir, then it's two Mimirs. Yeah, I want to use this slide because I often say Mimir, but the proper pronunciation is Mimir, just like the baby talk for sleeping in Spanish. And that's all. I hope you enjoyed the talk, and I'm open for questions. Otherwise, you can find us inside.
We've got time for any questions here. Any questions? We're all hungry for lunch. How are you hungry for lunch? This guy's had like 10 donuts. I'm not going to ask. God, that's a big number. We're not even going to say it for the stream. People on the stream should not know the number of donuts that you had. All right, let's do one more round of applause. Thank you so much. Thanks so much. So we are going to be breaking now for lunch, and we'll be back here at 2 o'clock for the last few talks. Enjoy. are gathered here today for some more talks, some more sponsor talks, and hopefully more donuts, not for you know who you are. No more donuts for you. I did hear there are still some maybe on the third floor, but I maybe cannot recommend that entirely. So yeah, let's get this party started here. We're gonna have, like I said, a couple more speakers, and then also after the speakers are done, so it'll be at the closing 4:45. Again, make sure to hold on your red ticket, the other half if you gave your other half to the Sox, for some giveaways and some other stuff from there. So, all right, without further ado, let's give a big round of applause for Biju.
Hey guys, all still awake after lunch, I hope. Good, so yeah, I'll try to fix that and put you to sleep as soon as possible. Okay, so as Pete was saying, my name is Biju Chako, and what am I going to talk about? So it's kind of a change of pace from what we've been listening to a lot over the last couple of days, which is how to deal with things as they get big and more complex and as you scale. But I sort of decided to look back a bit and talk about a tool we built back in the early days when we were pretty small. It's going to be a short talk, small talk about a small tool, but how that tool did really make some amount of difference, actually a fair amount of difference for us. So I'll get into a bit of story time and talk about what happened, for a few minutes only. Talk a little bit about the tool itself, and probably just close out with just a couple of thoughts, and potentially maybe a little encouragement for those of you at the start of this SLO monitoring observability journey. So yeah, that's what it's all about. So, but before I get into all that, let me just first make sure credit goes where it's due. This is my colleague Roshan. He's a good friend of mine. Now he's like the guy who was behind most of what we did here. Did a lot of the work, but thanks to COVID, he couldn't get a visa to travel, so he kind of left it to me. But yeah, so I'm not going to kind of imply that a lot of this was my work. It was his. And I'll probably toss out the disclaimer. Maybe I'm not going to be able to go into as much detail as Roshan would, but let's hope it works. So going on from there. First, let's set a little bit of context, and I'm hoping this is going to sound familiar to some of you. So three and a half years ago, when I joined Squadcast, which is a small, fairly early stage startup, which is even earlier stage startup at that point. It was pretty small. I mean, we were like 4 engineers. We were like, pretty small, no money. We had obviously feeling a lot of pressure from the VCs and from customers to actually have features that people wanted to use. And yeah, we were scrambling to just get stuff done. And when I came in there, I would say that, I think we were the poster child for every anti-pattern you could think of, right? I mean, we just hacked together some stuff and we were kind of pushing it out the door. There wasn't much, there wasn't enough testing. There's never enough testing, but this was really not enough testing. There wasn't, monitoring was very minimalistic and pretty hit or miss. And like, we were just so few people that we weren't in a position to, or rather, we were feeling that pressure to push features out, and all of this stuff was getting neglected. And predictably, this meant that our reliability story was fairly pathetic, to be honest. It wasn't so bad that we were losing customers, but it wasn't good enough to really build a lot of confidence in them. And we're an incident management tool. We're supposed to be more reliable than whatever you're monitoring. At least, and at that time, it was kind of hit or miss, and it wasn't great. It really wasn't great at all. And and that's when we kind of brought Roshan, who's a SRE. We brought him on board to help us just get that side of things sorted out and try to get us up to some point. And he took a look at things, and one of the first things he said is like, we can't just talk SLOs. We've got to walk that talk as well. We've got to really measure. We've got to really see where we're going, and and based on that, at least we'll know really where we are. Right now, we had something which was just, we know we're in a bad place, right? But we don't know exactly what that means. So he started wiring together stuff. A lot. Initially it was like a lot of Bash scripts and just Python, and just all wired together with baling wire and duct tape and trying to get something going. And we kind of started running into fairly basic minor problems, and it kind of says something about the place where we were, that even those things were challenges for us. We didn't have the bandwidth to deal with it. And I was getting a lot of pushback from management saying, okay, if it's not working, it's not working, don't waste time on that. Let's push out some more features. It's like, why do we want to push out more features if people aren't going to be able to use them properly, if they're not reliably usable, right? So we started trying to hit those problems one by one. I like to say we, but let's face it, it was basically Roshan. And basic stuff. First thing, right? Like I said, we were like 2 or 3 people trying to do everything. Now 4 with Roshan, and basically our monitoring at that point was just like a mishmash of different things, and they weren't really talking to each other. And that's not to say that they couldn't talk to each other. We just hadn't taken those steps. And so a lot of our SLIs were coming from, key things were coming from different systems, and it was just difficult to just visualize all of them at one place, right? And so that was probably one of the first things we started doing, and this is when we started working on, like I said, this mess of scripts that eventually became the SLO tracker application, right? So started pulling in things. Now, again, and this is going to be a theme that's going to come in, that's saying that there are probably better ways to do this, but we just wanted to get something quick and dirty and working as soon as possible, because the priority at that point was just getting something in place, right? So so we sort of fixed that, and I'll talk about what the end result looked like a little later. So that as soon as we started trying to get together data and trying to figure out the best way to do that, we ran into the question of how are we going to retain our data. So like I said, early stage startup, we're like burning our initial seed fund really quickly, because it wasn't too much to begin with, right? And we really couldn't afford to even desample. We couldn't hold on to all of our raw monitoring data for then. 90 days would be optimistic, I would say. I don't really remember the exact numbers now. But yeah, we just couldn't keep all the raw data. On the other hand, how do you know where you are, and how do you know if you're improving, right? If you haven't, if you haven't got that data. So we figured, like, at the very initially we were just talking about 6 months, 6 months, but we've kind of figured out. We took a call. We've got to have at least a year's worth of data to see how we're making progress. So we just needed a simple way to just retain just the data needed so that we could see how our SLO performance was. And we figured we'd deal with the other because realistically, I mean, monitoring data that we had at that point was used primarily for troubleshooting and stuff, and you know, after about a month, it's kind of obsolete anyway, because things were moving that quickly at that point. So we just wanted to do this. So we came up with this thing of just keeping just enough data to sort of model so that we'd have a record of how we were performing against our SLOs, right? And discarding everything else, right? And this is where, so at this point we were sort of collecting some amount of data. It wasn't super accurate, but it was at least giving an idea of where we were, and we started feeling that pressure of saying, okay, we are this far away from where we want to be. It was a big gap between, you know, what we want to achieve. I'm not going to toss out actual numbers for fear of embarrassing myself, but it wasn't great. It wasn't great, right? Yeah. So you know, we started trying to dig into this, trying to fix stuff, trying to figure out where the gaps were being created, and we realized that, you know, one of the significant parts of it was just false positives, right? False positives and false negatives to a lesser extent, right? One of the things that we were doing a lot of at that point of time were doing these distributed latency availability checks, like, you know, from around the globe, and those tend to generate a whole bunch of false positives, especially the checks that are sitting behind the Great Firewall of China. They tend to flake out for no real reason. So we were getting a lot of indications that, I mean, we were getting reports that the system was down or slow or not working properly. And, you know, when you studied it and we looked at it, we figured out that's not really true. So there's a lot of false positives there. We were occasionally also getting false negatives when you know, things were going down, and it wasn't showing up on any of our stuff. That was less common though, and those were mostly on, you know, more fine-grained kind of issues. So we really needed, again, now ideally you want to sort this out, you want to fix this such that you can trust the information that's coming out of your monitoring systems. That's the correct thing to do. But, you know, sometimes and in our situation at that point of time, we just had to sort of grin and bear it and try to work around it at that point. And yeah, so we needed to figure a way of just quickly toggling the validity of some of this data that was coming in. Because, you know, first we obviously built the ability to mark things as false positives, and then we realized after a while we were probably getting a little too aggressive in marking things as false positives. It's an easy way out, right? Yeah, there's nothing really wrong. It's monitoring is bad, and yeah. So we kind of figured out it's not just a one-way thing. We've got to be able to push it back and forth as we realize as our picture gets better and better. So yeah, so that was another problem. And yeah, so we needed to be able to sort of tweak the data. Again, not ideal. You really don't want to be messing around with your data after you've got it. But in this situation, that's you know a slightly more accurate picture. You know, better picture of where you are was probably more important at that point of time than having, you know, exact accuracy and so on, and being you know, theoretically or you know being technically correct, right? So I mean, these were like, again, none of this is brain surgery, right? None of this is stuff that can't be figured out, but we're talking about a situation where just deploying that, you know, focus time to sort these things out was a challenge. So yeah, so it started off initially as a bunch of random scripts and stuff that we tried to, you know, we kind of consolidated into an application. which we, with great creativity, we decided to call it SLO Tracker, which, and it basically just, the idea was to essentially just embody it's something quick, dirty, simple, just to to work around the problems we are, to give us some indicative direction. So, for example, in terms of the data we were collecting, we were basically just interpreting alert information coming out from our monitoring systems and using them as boundaries and marking windows of outages on and that's what we were using for measuring our SLOs, right? But we were, it was fairly simple, fairly quick to build out, and it gave us what we needed at that point, right? A single place to see everything, right? Handling all the various SLOs that we had, being able to deal with false positives, right? By toggling them off as needed, and occasionally creating records of breaches that we didn't catch. Some basic analytics in place, right? And it was very quick, very easy to deploy. It didn't really add on to our operational overhead as one more application to manage. It was pretty one, a little bit a simple MySQL database and a Go executable, and we were going on. And it kind of integrated well with mostly the couple of tools that we were using, and now probably a few more that some of our contributors elsewhere are using. So we basically worked in a we used a sort of push mechanism from the monitoring tools. They would call out webhook integrations and update us whenever something went wrong, and that's how it works. And for some of our more homegrown tools, we exposed an API to start collecting the same stuff. So again, very, very simple, very basic stuff, and I'll probably get to the impact of this a little later. Let me just quickly go over the tool itself a bit and tell you a little bit about. So once it kind of started working reasonably well, we put it out there for other people to try out. We've been, it's been more or less, staying the way. Now that's kind of doing what we needed to do. But I think that it does have some fairly significant, it's got some limitations which probably we need to sort out if you want to, get more broader usage. As of right now, it's just a single user system. We don't have multi-user. Forget about multi-tenant. It doesn't have multiple users. So that causes a number of issues around how it works, especially around the question of being odd. One thing now is that obviously this SLO data is kind of critical in terms of deciding a lot of things about some of our engineering planning. It also sort of impacts what the performance of some of our teams and so on. So the lack of an audit trail on that is probably not great. It's not been a problem, but it is something that we've been thinking about. If for other people to use this, having a hosted solution might be nicer. The calculation at this point is of SLO performance is kind of, it's very simplistic. So if you are getting information about the same outage from multiple monitoring sources, it's kind of double counted. That's kind of easily sorted. But right now, since it doesn't happen a lot for us, we just kind of manually sort it out by using by toggling it off as a false positive. One of the reports as a false positive. But yeah, again, not ideal. It's things we need to fix. So we do need to fix that. Other than that, a couple of other things that we need to sort of quickly do for this very small, very minimalistic application. One is just having some kind of hierarchy there so you can organize it. Obviously, somewhat larger than we were when we started working on this. And now trying to just segregate different people, different teams' concerns. It's nice. It'll be nice to have that kind of hierarchy. It's not, again, we're still pretty small, so it's not a big problem. But I think it's probably a blocker for other people to adopt it. Yeah. Right now, again, all the reports are on kind of fairly fixed windows. So we probably want rolling time windows as opposed to just month to date or quarter to date and that kind of thing. Arbitrary time periods, if you want to just see how things are going. We don't really do that very much. When we want to do that, that's usually more troubleshooting information that we want to do in our monitoring tools. But I guess some of our users, external users, have mentioned that they're interested in that, so we've asked for patches. Well, keeping our fingers crossed. Audit logs, something I mentioned earlier. I think that's probably important. That's probably something we will work on. We are also getting bigger now, and I suspect we may just move on to something else. I don't know, but as of right now, probably audit logs will be helpful as the team gets larger, so that we don't have people stepping on each other or accidentally corrupting data or something of that kind. So yeah, that's a little bit about this very small tool. I mean, I would like most open source projects we need a lot of help. So one thing is basically nobody's heard of us. A few people have used it, but yeah, if you guys can try it out, I mean the links are here. Just go take a look. slotracker.com. That's fairly easy to remember. Take a look and try it out, and feedback is what we need probably primarily. Patches would be great, but feedback is good too. But this talk isn't primarily about the tool. It's a small tool. I mean, I suspect most of you here have probably spun up something of equal complexity very quickly as well at some point or the other. We're not. I don't claim to be some kind of path-breaking way of doing things. It's just a quick and dirty solution to our immediate problem that we had. I mean, happy if you use it. That'll make all of our lives easier. But that's not all primarily what I wanted to talk about. I wanted to talk about the impact of doing this, because we were really debating this when we started on this, right? And there was this conversation of, look, let's not start off something half-assed and have to redo it later, right? Let's if we're going to do it, let's do it right, for specific values of right, and everybody's definition of that was different. And honestly, we were in a certain amount of paralysis around this. But once we just decided to put our foot down and measure things, and yes, acknowledge that these measurements were indicative, not super accurate, right? And just started using that as a gatepost, actually trying to push back on deploys when our error budget was mostly consumed, and it started the conversation, right? And especially amongst the developers, they started feeling that back pressure, that was impacting their productivity, because until the thing gets into production, obviously they're not done. That started, we started thinking about reliability, and ideally we were thinking about reliability in something other than a postmortem, right? Historically, that's what we were doing. It's like, oh shit, something's gone down. That's when we think about, oh, we should have done something about that. So it was moving towards the front of mind, right? We started doing basic stuff, trying to do more risk assessments, trying to figure out how much impact, especially like some of the big feature deploys, what kind of impact are they likely to have? How risky were they? So once we started, moving forward, things started improving, and which meant then, the bottleneck or the biggest set of problems started moving into different parts of the process, right? So that's when we started thinking about, okay, now if we're going to hit our objectives, we're going to have to think about improving our testing, improving our monitoring, right? Because now it was visible, right? The impact of that was a lot more visible than it was before. As we got better with those aspects of things, we started thinking about other things like incident management, which is good given that we're an incident management company. But we started trying to figure out, okay, what can we do? And I think these, like I said, so this was like a first step, right? It's like a small constraint over there, and that just started. It had a sort of domino effect going backwards through all of our processes and trying to forcing us to think about what are the different ways we can try to improve our performance, improving our processes across that, right? And so that's what we learned. So we started figuring out, right, that we looked at SLOs at that point as primarily a gatepost to start of improve the quality of our deploys. But I would say that fallover effect, that domino effect on our overall processes was probably a bigger impact for us. All right. So I have some amount of background in Lean and there's this concept in Lean of stopping the line in Kanban, for example, of stopping the line when a defect is discovered, right? Of creating back pressure in the process, right? And I've kind of started understanding SLOs as a sort of unambiguous way of doing that, and I was surprised. I was surprised to see how much it was forcing us to improve across the board, right? The other thing is just be pragmatic, right? Especially when you're a small team, when you don't have much budget, it's often difficult to get into grand schemes of significant process change, significant tooling getting deployed. So it's probably best to just get something out the door, and quick and dirty is better than elegant and incomplete, right? And it's okay to compromise. It is okay to compromise as long as you're committed to eventually sorting that out down the line, right? And I don't know what the picture is in wherever you guys are, but talking to a lot of people in Bangalore where I am, for a lot of companies, SLOs are still in the realm of the theoretical. Everybody likes them in theory, and everybody's ignoring them in practice, right? And a lot of it is driven by these kinds of things. One, just analysis paralysis. It's not yet the right time, or we don't. It's going to be a huge job to get all this stuff in order, and that's what I'm trying to tell people. It doesn't matter if you've got some ancient legacy system with that's in a real mess, or whether you're just starting out, it's new code with nothing in place. Just do something. Get something in place. I mean, a tool like SLO Tracker will probably help you. You don't have to use it, but the idea is just start. And once you start, and you're disciplined about it, the pressure that of recording what you're doing and looking back at will force you to improve things across the line. Yeah, that's what I had to say. Questions? I see I've succeeded in putting you guys to sleep. Okay.
Any questions? Anything from the top? All right, great. Thanks so much. This is fantastic. Thank you, guys. See you guys. All right, we've got the last three, but not least, sponsors of this wonderful event. Again, make sure you make your way through. If you need some new socks, it's been a while. It's been a while since you've been to a conference. Your socks probably have holes. You should get a few pairs, and there's a few sponsors that will give them to you happily. Our first sponsor up, you know him. You may not love him, but he's here.
Oh, nobody likes me, Pete. That's the beautiful part of all of this.
Duckbill Group.
Where did he hide the HDMI thing?
I actually love specifically. I'm not even going to ask for you to clap. Please
No, it's better.
don't.
It's better in many ways if I don't. That's what makes this whole thing work. So, not that one. Good, good, good. It's there as a warning for the Armory. Thank you. You're a gentleman and a scholar. Let's see if we can make the magic go.
All right. The Duckbill Group.
All right. Thank you. This is a man-made substance. It's called plutonium-238. 1 pound of it costs $4 million, not including startup costs to build the reactor in the first place. It's used in weapons, in interstellar exploration, in medicine, and it's apparently what they make the AWS managed NAT gateways out of, because holy God, are those things expensive. This is, and I am not kidding, this is not a shitpost, how data transfer gets billed in AWS. I put a picture in the Slack team, so don't feel you have to panic, take pictures of this. I have seen this picture printed out and hung in cubicles at AWS offices in Seattle because they don't know the answers either. It's great. Let's move on, we're on a time budget. This is the AWS Snow Cone. It holds up to 14 terabytes of data, has an e-ink display, weighs 4.5 pounds, and has to be plugged in at all times to work, meaning that this is without a doubt the absolute shittiest Amazon Kindle e-reader that they have ever made, much less shipped. You rent it by the month, which means that at that point you figure out its cost on a new pricing dimension. It's not that economical when viewed through a lens of gigabyte pound months, which is, sure, admittedly a ridiculous way to price it, but is it any more ridiculous than the way that Amazon already prices all of their things? No, my friends, it is not. This is the famous Schrodinger's cat thought experiment, or an illustration thereof. A cat is placed in a box alongside an overcomplicated device, probably made out of lambda functions. It has a 50% chance of triggering and killing a cat during a particular time window. Until you open the box and observe the cat, there are 2 cats. One is alive, one is dead. Then you open the box, observe the cat, the quantum waveform collapses into one of 2 states, and finally you are billed $400 in Amazon CloudWatch fees for having dared to observe something. I'm Corey Quinn, and I am the Chief Cloud Economist at the Duckbill Group. What the hell is a cloud economist? Well, I'm a lot of things in case you hadn't picked up on that, so let me instead tell you what I believe. I believe that finance and engineering need marriage counseling because they both care about the same things and want the same things, but are great at talking completely past one another. I am the cat eating the flowers in this particular analogy. Finance doesn't usually care about people spending too much money on AWS. They care about predicting it and making sure that they expect what the charges are going to be. Cloud finance is an engineering problem. It is not a finance problem. Along that axis, I also believe that cloud cost and architecture are one and the same in the world of cloud. I was quoted in his presentation this morning from an AWS thing and was only told after the fact because I'm right. We are a bunch of engineers who just happen to speak finance, not the other way around. I also believe that if I'm going to rip you off, I should do a really good job of it and not try and do the small parts along the way. And that means a lot. It means that our conflict of interest avoidance is intense. We only ever do fixed fee work, for example. We do not bill by the hour because it will take forever. And we don't charge a percentage of savings because then we'll tell you to delete your backups, which, while entertaining, is probably not in your best interest. We do no implementation work. We are purely advisory. We are not going to touch your production code. If you've ever seen my code, you can thank me later for that. We also have no partners, because when we recommend you do something or don't use something, it's because it's what we believe, not because we're getting money to say that or not say that. We also believe that humans make pretty shitty computers out of themselves, but foundationally, that understanding, predicting, and understanding AWS spend requires human beings assisted by software, not the other way around. Computers and also a disturbing number of engineers miss business context completely and make poor choices as a result. That's why we're here as a consultancy and not trying to sell you software that doesn't work. We also believe that we can't teach how scale works. That's why we have that's why we don't have new graduates. We only have senior people who know what they're doing because we built things at scale, usually badly, and learn from the experience. That's why we teach people through experience rather than doing it by a case study. Speaking of case studies, our clients love us and say nice things. This is one of my favorite quotes, no less so because it comes from Charity Majors of Honeycomb. Those people are smart. They know what they're doing. Their entire team does. And this is why we focus just on AWS, because we are actually good at doing this one thing almost to an obsessive degree, which makes us socially unpleasant, but very good at this. Honeycomb, Instana, New Relic, 3 companies that were here this week have all been our reference customers. A bunch more have also been kind enough to let us invoke their names when talking about what we do. What we do is effectively 3 things. We optimize your bills via exhaustive, in-depth analysis. We find the savings and predict your future. We negotiate with AWS on your behalf in hilarious and fun ways that they mostly enjoy. And of course, we will spend half a day with your team just laying waste to your bill and being astonishingly funny as we go. If you're still here and listening to me, great. Come to Momo's tonight at 7 o'clock. We're hosting a drink up if you have nothing better to do. We'll be entertaining and fun. I'm Corey Quinn of the Duckbill Group, and I cede the remainder of my time to the representative from Date a Dog. Take it away.
Thank you, Corey. Always fun and informative. I'm actually I have worked. I was a salaried employee of Duckbill Group, and I think Mike and Corey will have to confirm for me. I think I am the only person who has actually quit from the Duckbill Group. And I think specifically why Corey likes to bring that up is because during COVID, a lot of companies would say like, oh, like if you have people quitting after COVID, that just shows your culture. And I was like, no, it's not. It's not them, it's me, I swear. So, all right, let's give it up for Rick from Datadog.
Thank you. All right, hello friends. As mentioned, I'm Rick. I'm on the community team at Datadog, and we've been spending a lot of time talking about work for the last few days, and so I'm going to talk about anything other than work. So I do work at Datadog. In my day job, I spend a lot of time dealing with different products that we have within Datadog, different technologies that we integrate with. I get to spend a lot of time looking at really interesting and neat problems, but I go home at the end of the night, at least mentally, I work from home. But so do all of you, right? You're all people, you have hobbies, you have interests, and so I started to think, how can we apply observability to our hobbies and our interests? Can we kind of co-mingle or co-opt our work, maybe for fun? And so during COVID in particular, I spent a lot of time playing video games. And so I was dumb enough to admin some servers and then spin up and own some servers. And there's a lot that goes into making that ecosystem. And so I was actually able to gather some of the metrics and some of the logs and apply some synthetic tests to a video game and really build a better community for my players. So was my game available to them? Was it performant? I got to learn about the players. Where are they coming from? They're coming from all over the world. That's really empowering when you're in this remote-only kind of place. And then also, what are they doing in the game? What's their behaviors? Are they more interested in a certain style of play? Are they consuming things from the bot shop that maybe make the game a little too unbalanced? And then additionally, do we have bad actors amongst us, right? So I'm actually able to look at some of the logs and see, are they coming in from VPNs? Are they somebody that we had banned? There's some knowledge sharing that happens between the different game owners. And so observability really made that easier for me in my personal life. And so another example of observability is a Datadog employee bought an old sailboat. And this sailboat had a bunch of different instruments inside of it that collected bits of information but were in no way connected. They were just disparate solutions, not uncommon to some of the things we do in tech, and they were able to combine those different pieces of equipment with a Raspberry Pi and some LTE connection, and they actually were able to make a monitoring story for their boat. And it seems like, maybe that's just for fun, but they also had a really useful safety use case for this. They were able to share their logs with their location with their loved ones, right? And so they've actually been able to apply this to a very physical hobby that you wouldn't really think about being tech. And so another example that I really like and some members of my team we're into home automation, right? So we're automating the physical world around us. We're using our geek powers to adjust our temperature or maybe our shades or whatever vanity thing we want to do. We obviously track that, right? We're passionate about the observability, so we want to have pretty graphs and charts to go with that. And so thinking along those kind of lines, a member of the Datadog community a couple of years ago had some issues with their power provider down in Texas. And you might have seen this on Twitter at one point. I think it looked a little bit different a couple of years ago. But they were actually collecting the health of the electric grid, the exchange rates that were happening with the cost, and some of the outages that were happening. And they're using this to build a case in the open about what was going on in their real world. And so I share this not to make an inference on this utility provider, but if we could think about how we can use observability to enhance our own personal lives or our own personal communities, that's an easy win for all of you, right? These are things that you're passionate about, and there's probably some opportunities for you to expand and bring that out into the real world. And so we would love to hear more about the things that you're doing with observability, particularly for fun. So if you want to hit us up on the Monitorama Slack or the Datadog Slack, please reach out. Thank you.
Alrighty, thank you. And our last sponsor is going to be Cribble.
Thank you. All right, thanks everybody. All right, perfect, yes, a little taller. Hello, welcome. So I'm Clint Sharp, co-founder and CEO. I spoke yesterday, here to talk a little bit about the things that we sell, because in addition to building some open source software, we also have a number of commercial offerings. Cribble, our flagship product, is called Cribble Stream. It is an observability pipeline. Its job is to connect anything to anything. Let's say that I have an arbitrary agent out there. It's FluentD, it's Beats agent, it's a Splunk Universal Forwarder, it's Prometheus, it's the Grafana agent. I can take that and make it talk to anything. Make it talk to Splunk, make it talk to SignalFx, make it talk to Datadog. It does not matter where the data comes from or where the data goes to. It is very simple to glue all of these things up, reshape that data, enrich it, aggregate it, convert logs to metrics. In general, munge all of the data in the pipeline in order to control cost and connect things that weren't originally intended to be connected. I'm gonna do a quick demo because I'm a glutton for punishment and I did this yesterday and I like showing off actual product. So one of our other products, Cribble Edge, is actually the agent itself. We actually shift that pipeline work all the way to the left. We make it very easy to auto-discover log data and ship that data off to wherever you would like. So in this example, I have a container which is running my Edge software, which I installed over here in advance, just because I wanted to do it in the interest of time. I'm going to navigate to this Edge node, and one of the things that we allow you to do in Edge, as an example, is we'll give you detailed performance metrics of what's happening. All of this data is already being shipped off of this agent, and we can send that data to anywhere. In this case, we're sending that data to Prometheus. So I've got metric data going to Prometheus, and I have log data going to S3. And in the course of this demo, we're going to pick up some new log data, we're going to reshape it, and we're going to send it to Splunk. If you look over here in Grafana, I already have all this data flowing in here from that agent. It automatically, we have dashboards built for Grafana, so we make it very easy to grab the metrics. And the same agent also grabs the log data. So over here, we have an automatically configured set of log data that's being picked up automatically on the file system. I didn't have to do anything. It actually finds all of the log data that's being written by all of your applications automatically, so that we can pick up, for example, this access log, or this is being written by Cribble, or in this case, oh, actually I'm on the wrong box. Let me go back to, I meant to go here. And we also can explore what's on the machine as well. So I can explore, see all the processes that are running. As an administrator of a logging solution or any type of solution, really trying to understand what's happening out there in the world, I want to be able to see which processes are running. I want to be able to see which log files are being written by those applications. I actually dive into that log data and see on that machine that this is indeed something that I want to pick up and I want to configure and ship off. So we're doing that. We actually like what we see here. We would like to be able to ship this off to, let's say, something like a Splunk. So in order to do that, I'm going to go back into my fleet, and I'm going to go over here to collect, and I'm going to add a connection here and ship this data. Oops, I don't have a destination here for Splunk. Let's search. I'm going to add a new one. Ooh, that failed. JK, all right, let's go back here. Manage Edge. I'm gonna run out of time failing, but that's okay. We're gonna have fun doing a live demo on stage because this is what everyone loves to do. All right, add Splunk. Gonna make it called Splunk. The address is indeed named Splunk. I'm gonna hit save. And now all I need to do in order to get that data flowing is just drag and drop this data over here. I'm gonna right now send that data pass through. And pass through. And all of our configurations are backed by Git. So as I'm making changes, actually there's just YAML files sitting below on disk, and we're showing you in detail all the changes that we're making. You can revert these changes easily. You can integrate this with an external Git repo. So figuring out how to manage this and maintain configurations is all handled for you in the solution. So I'm just gonna say adding Splunk. I'm gonna commit and deploy that data, or that configuration. And if I go back to my fleet here and I look at my workers, you'll see new configuration versions are being shipped out to those individual agents. So we're managing these agents, up to tens of thousands of these agents out there in the field. You can also do this with your in the stream. So right now, everything I'm showing you, I can do the same with my agent or with somebody else's agent. So I can use your existing agents, or I can ship you an agent of my own. Yep, one more. And if I go look in Splunk, in 1 second. And I'm gonna go search. Skip that. Index equals main. And that data that we were looking at there, the temp big JSON, already flowing into Splunk. So very, very simple to easily connect this. I'm running out of time to reshape some data, but I can come in here and drop methods out, I can drop fields out of the JSON, I can enrich this data, I can reshape it and do whatever I would like to do with this data in flight. So very, very simple to get the right data to the right place to help you control cost. If you ask me what Cribble sells, fundamentally it is choice. We are giving you the ability to take anything and send it to anywhere, to be able to control what's going there, the shape of that data, the cost of that data. And fundamentally, we're helping solve the problem between data growth and budget. Your data is growing at a 25% CAGR, your budget is not. You're gonna have 2.5 times the amount of data in 5 years that you have today, and you're not gonna have 2.5 times the budget. So how do we take next generation approaches about getting the right data to the right place to help you fundamentally run all of your observability software that you need to in order to be successful as an enterprise? And that's it for me. Thanks, everybody.
Awesome. Great work. Big round of applause, honestly, for all of the sponsors. Hopefully you all got out there and check them out. This event would not happen without them, so we really appreciate all the sponsors that are here. All right, let's bring out our next speaker before break. While he's getting set up, again, remember your ticket. I've seen the prizes that are in the back that are coming with these tickets. May or may not include like 14 bags of coffee and other coffee-related prizes, and maybe some other stuff. I don't know. I didn't dig through the bag that much, but definitely like a lot of coffee. I may just start shoving coffee in people's bags if you leave them unattended. So, all right, let's give it up for. Oh, not yet. Come on, you can get there.
Oh no.
No, it's fine. It'll come back. I wanted to have. There we go.
Oh, sorry about that.
We'll just choose because they'll totally work.
That's okay. Oh, let me just go. Yes. Sorry about that. Yes. Oh, we almost had it, and then we lost it again.
All right, let's give it up for Arda.
Hi, I'm Arda. I'm a software engineer at Meta. I've been a full-time employee for 3.5 years, and before that I was an intern at the company. And this is my first time giving a talk externally. I give talks internally to my coworkers. That's why my manager actually had to meet me multiple times prior to this meeting to make sure I don't give out company secrets. So I tried to like remove the numbers, but it's still quite interesting in my opinion. So yeah. So what are we gonna do? What am I gonna talk about today? So first, we're gonna do overview of detection at Meta. I'm gonna talk about our system architecture, quite just an overview, not in detail. After that, we're gonna go into our first big problem that we faced, which is our alert overload, and how we try to reduce the noise. After that, we're gonna go into the second biggest problem that we faced. Biggest, like all the problems are big, but improving incident time to detect. So this is whenever an incident happens, how fast are we able to detect it and how we can improve it. And then we're gonna close it up with challenges on the horizon. What are we focusing on in the next coming years? You know, my company is moving towards metaverse. What does it mean for us? Not that detailed though, just, you know. Okay. Overview of the detection. So I wanted to talk about a little bit about the data sources that we support. Oh, great that you have you can see that. So we support time series. We maintain our own monitoring stack since 2009 is when, yes, 2009. But yeah, the time series database, we have ODS, we support our data warehouses, and we have structured logs, Scuba. and we have unstructured logs logarithm. So we are able to detect all these types of data sources. And what are we using this detection for? So first and foremost, we have data centers across the world, and we would like to get alerted if temperatures go high, if something bad happens. So our services are deployed in these data centers. The second one is the infra services and pipelines. So this is your common availability, error rate, all that fun stuff. And then the last one, not the last one, but the other big one is the product metrics, which is, let's say you want to get alerted on if something happens on Instagram on a particular OS in a particular country. So you are able to do that with our system. Detection intelligence. So here, I would like to talk a little bit about what a detector is. So detector is what we call these objects, detection objects. They have a query that can return multiple time series, and they have a list of thresholds, which they execute. And then depending on these thresholds, they submit alerts. So at Meta, we give our, because this is internal, we give our customers, other engineers and data scientists and staff, this is actually a screen grab from this morning. I wanted to make it as modern as possible. We give these options. I'll go over. So you have the static threshold, which is your classic, alert me if data goes X, or do something if data goes below Y. And then we have our univariate algorithms, which act on an isolated time series. Here we have predictive analog algorithm, which is developed by an Israeli startup, and also we have our own in-house algorithms. We have slow drift, we have reference deviation. So these are used to detect spikes, these are used to detect regressions, and these are used to, I believe, detect whenever there's a trend change, seasonality change. We also have multivariate algorithms. One you cannot see here is the global model that we maintain. We tune it for our use cases. And the other one is cohort divergence. This is, I'm not going to go into detail because these are developed by our data scientists, and we as system engineers, we take it and implement it. All right, some cool numbers. Scale of detection. So at Meta, we have 2.1 million detectors. Now you guys know what detectors are. They're just your objects that can execute and monitor your metrics. We monitor 300 billion data points per day. We submit around 1 million alerts per day, but only 20,000 of them give notifications. Notifications can be your robo-dial, your robo-SMS, your internal tool tasks, email, whatever you can think of. And yeah, there's a discrepancy, but why? We're going to get to that later on. So yes, system architecture. So this was the one that I was really excited about because, and then this was the one that got stripped a lot of info away from, but I'll still go into it. So we have our detection backend, and then detection backend loads configs from our detector config storage. We do this periodically so that we get the most up-to-date configs that people create. This can be either done by our UI, or people can go and write their Python scripts, their whatever they want. Then when we load these configs, we execute their query. Like we said, detectors have queries and a set of thresholds. So this query can be anything from our data sources. And in the arrow, you see time series data. So you should be asking, wait a minute, you mentioned warehouse logs, but why time series data? So all the data sources that we support have a native pre-processing inside, which then turns their data into the time series, and then we grab the time series from them. So we don't have to deal with that as detection backend. That responsibility is up in our data sources. And then once we acquire the data that we need, we submit it to our ML infra. Here, the data, we get back a trained data, and also this helps us train the model that we use to get the evaluation data back. So this is what we call online training. But when we do online training, a lot of things can happen, requests can fail. So we also have another mechanism that plays a catch up, but it improves the quality of the model, which is called offline training. And that's the amount of detail I will give about that. And lastly, we have the event storage, which we submit our alerts to. So that's the thing. The detection backend does not do anything but it submits a JSON struct that is then alert. And then your notifications, your robo-dials, all the logic, everything gets executed on another microservice. And I would like to mention that our service runs lean. This covers all of Meta, and it's only 200 machines. So it's pretty interesting. I wish I could give more numbers. Yes, so that was the overview of detection at Meta. And then now we want to keep improving, right? Because it's in-house, we don't use anything, we don't have the cool features as you guys have. So our challenges are different. We have to support legacy and all that cool stuff. So the challenge we had was how can we reduce noise while increasing detection coverage?
So noise here, because you saw the numbers, right? Like 1 million alerts per day, that's a lot. And 20,000 notifications, still, if you have 300, 400 on-calls, that's like 5, 6 tasks per on-call per day. That's a lot. So yeah, reducing alert noise. So this is what we call, oh, before that, like I mentioned, 1 million alerts and 20,000 notifications. So what happens to the 98% of that? So at Meta, we have a service called FBAR, which is Facebook Automated Remediation, which actually acts on these alerts. Like if there's an alert about restart, it will restart the machine. And pretty cool other logic it can execute on. So 98% of our alerts go to our automation systems. And then the 2% gets to wake up people, gets to bother them. But yeah, so how did we get here? This image was recommended by my manager. But I told him that I don't understand it because I did not grow up eating frog. But he told me like to tell the story. So what does it mean? So the story of the frog and boiling water is the frogs don't understand that they're being cooked alive until it's too late. So kind of it was the same story. Meta grew exponentially from 2008 to 1,000 employees to 2021, 72,000 employees currently. So whenever there's a new employee, whenever there's a new approach, people thought that was the new normal. That meant that whenever we had noise build up, nobody wanted to tackle it because there's more other problems to tackle. So yeah, so that's why we see like we see the condition we see today: 1 million alerts, 20,000 notifications. So we said, okay, wait a minute, we can do something about it. We're all engineers. We did our studies. So we actually we tried to find anti-patterns in detection, and we boiled these down to 7. I will not go into detail on what they are, but I will give example of 2 of these: Flappy and Groupie. I believe and if you have questions about how we did these, please find me after the talk. I will be able to give some information. So what is Flappy Alert? We actually had an example of this in another talk, I think on day 1. This is your metric, pretty cool. You have your boundaries and thresholds seem reasonable. You as a human, you set this up, you present it to your team, you're proud, you have detection, yes. But then what happens over the time is your data can move and then your thresholds cannot catch up. These are static thresholds, by the way, dynamic. This is one type. So this might just end up adding a lot of noise. And here, all those red lines you see is, again, this is a string graph from our internal service, and all those are alerts. And this team is not a happy team at this point. So what can we do about it? Well, let's have robots go in and analyze. So we wrote scripts that actually take a lot of data. They take detector configs, they analyze the data that they act on, and they change the thresholds as such. We call this AutoTune, and it's been pretty widely adopted. I believe after we released this, 40% of the employees that had detector configs used it in the first couple months. So that was a pretty good success story there for Flappy alerts inside the company. And for Groupie alerts, what do we mean by Groupie here? That is when multiple alerts fired for the same issue. So you can have like, for a service, you can have error rate, availability, latency, XYZ, but then something like some bad diff gets in and then it keeps crashing. Are you gonna receive an alert for everything? Probably you're gonna, because that's how you set it up, right? You wanna get alerted on the last second possible. So, but then that means whenever something like this happens, you get a lot of alerts. So we said these are Groupie alerts and we can do something about it. So we released this new service called alert aggregation that specifies a rule. And then with that rule, you can basically group all the alerts you want depending on the dimension of the alerts. What is dimension? It's just a set of strings. Yes, and I will not be able to get into that. So yeah, those were the 2 examples. And in the end, we marked these. We said, okay, there are 7 anti-patterns. So what do we do with them? We built this other platform called Alert Doctor. So this is an end-to-end platform. You will see all your team's detectors and everything in this one nice UI, and then it tells you whether, you have unhealthy detectors, and if it can, it shows you what actions you can take. So with these, we actually, we identified 24% of our detectors to be unhealthy at the time of our work. And with after releasing Alert Doctor, in 4 months, we saw a decrease to 11.2%. That was pretty impressive, even by our internal standards. So yeah, we were able to kind of cut down the noise for our teams and hopefully improve their productivity. So yeah, that was the reducing alert noise. So now it's improving incident time to detect. So MTTD is mean time to detect. Incident mean time to detect is much higher than acceptable. at Meta, for our current standards, I heard throughout the past 2 days, I heard brilliant numbers. That really motivated me because for us, it's not, the grass is not that greener always, given the amount of things that we have to support. So automation detects 10 times earlier than manual methods. This is you're looking at the dashboard, looking at metrics yourself, trying to do data. But less than 50% of incidents are detected via alerts at Meta. So we continuously working on this. But then recently we made this one of the critical priorities, and we looked into it, and then we came up with three buckets of the reason why we're in this stage right now. The first one is the limited visibility into monitoring effectiveness, lack of clear reliability metrics and goals, and ad hoc and unstructured setup, given how Facebook/Meta was in its early days, and given how we still need to support whatever is built back in the day. So what do we do with these? We basically said, okay, let's take these problems one by one, and let's try to come up with solutions that we can execute on, and then we can disperse in our separate teams, because we are in a microservice architecture with different teams maintaining different parts. So for lack of reliability metrics and goals, the monitoring teams came together, and we established SLIs, SLOs, and set criteria inside the company. For ad hoc monitoring setups, we've started the project of out-of-box monitoring. For limited visibility in terms of what happens to the metrics, we started alert quality metrics and dashboards. So I'm going to go over the solutions right now, the following slides. So for SLI, SLO set criteria, we actually published in our production engineering blog a service called Slick that does this at Meta. So you'll be able to find much more detailed information there. But basically, to make sure people adopt these, we had to champion this effort. That meant that we had to pull people in, educate them what SLI, SLO mean, because these are brilliant software engineers, but they have no idea what these things are, because they're relatively new terms. So we had to educate them, we had to identify champions, and we had to make sure they were using best practices, and they were basically broadcasting them inside the company. And like I said, our production engineering blog post has a really cool content about this one. For out-of-box monitoring, when you set up a service, artifact, pipeline, anything, because people love setting things up, and we give people complete control. So there are no limitations at Meta in terms of what you can do in that. But so when you set those things up, you might not be the best person to set up your monitoring as well. So we said, okay, let's actually start out-of-box monitoring. So now we do continuous health checks. We do data quality checks. If you're a data person, if you ingest data, if you store data, anything, automatically we say, yo, you're doing a bad job, or you're doing a great job, keep it up. And then, yeah, we still keep our efforts on out-of-box monitoring to make sure people don't need to acquire as many domain knowledge as we monitoring people do. And the out-of-box tooling. So these are the tools that we provide to our platform teams inside Meta, because as almost everything is in-house. That means people need, whenever there's a modern tool, we need to provide them the same inside the company. So for our platform teams who actually have products inside the team that other teams use, we came up with a template system where the product team can specify, this is my product, this is how people should use it, and this is what an error looks like. And then they specify what the customers of that product can change. And then we set up detection like that. We call this DTS, detector template system, built for my coworker, I love. Distributed bulk backtesting. So this is, okay, you build all these monitoring, and you when you build these, you want to test them, but you probably don't want to test them in prod live. So we built a distributed bulk backtesting that is pretty performant. And on top of this, so all of these detection methods are maintained in a pool-based method. That means I have a query, I execute the query, I get data. Data does not come in. On top of this, because this was the limitation for the past 11 years, we built a service that does push-based detection with the same infrastructure. So this means we can actually cut our time to detection to mere seconds instead of having scheduled configs run. And for the last one, alert quality, alert metrics, and dashboards, we actually started digging deep into what can we do for our alerts to make sure they are actually good and useful. And we started coming up with terms in terms of what makes an alert useful. So we said if an alert is being interacted on, that is, if an alert creates a task, if an alert gets suppressed, if an alert gets acted on, it's a useful alert. So starting from there, we built upon the dashboards and the metrics, and we told people you have some alerts that you do nothing about. So that also helped with the unstructured way of setting up monitoring. All right, I don't exactly not sure how I'm doing on time because there's nothing that tells me that. But so challenges on the horizon. These are the things that we would like to see. We are going to be working on. So the first one is the scale challenges from anticipated growth. So we, as the monitoring team at Meta, anticipate there's going to be a 10x of detectors in just by the end of 2023. I mean, we have we know what projects are coming up. So, and on top of it, with the current ML infra, there's going to be 100 times more detectors using our ML infra to do detection. That is dynamic detection, the univariate, multivariate. So our first challenge is to make sure we can scale naturally and we don't have no downtime. So that means a lot of work and reliability. That means a lot of code. And the second one is ML monitoring. You might be asking actually, like, what is ML monitoring? So the ML models that we use at Meta, this is not just for like systems, but this is for your Instagram recommendations, your Facebook, your WhatsApp, whatever. All these are trained with thousands of labels, and their the graph is pretty big. So it's not as straightforward as monitoring a system. That means it has its own set of complexities that we haven't had a chance to attack. I mean, we haven't, as in we are attacking them, but we're going to be focusing on that. Don't quote me on that, but like you're working on it. But yeah. So long story short, we're going to be looking at the model performance issues, which are really hard to detect and which cost money, huge amounts of money if something goes wrong. I'm not going to give any examples, but you all know how this works. And the other one is the ML pipeline complexity, given how complex our training models are. Whenever there's an issue, they usually go silent, and we detect these like sometimes months later. So we're going to be focusing on ML monitoring. And yeah, so hopefully we are on our way out of the boiling water. And thank you for listening. Yes, I will take questions. I see your hand.
I think you mentioned you have two types of training, offline training and maybe online training.
Yes.
Talk about what's the different time periods on which those trainings occur.
So the question is, you mentioned online training and offline training. What is the difference? So online training is trained with the data. When your detection config runs and acquires data, it pushes that and gets a trained data. But that same push, that whatever limited time of amount of data, new data, we say, gets ingested in the model. But offline training takes a huge chunk of data and trains the model so much so that if there are any issues, because like I was mentioning, when we do online model, there might be some issues with the request. You might have like one request might have like some missing data, so we can train it wrongly. Offline training makes sure we catch up if there are any issues. And
how long does the offline training usually take?
Can I say anything about that? Oh yeah, the question is how long does it usually take? I am directed to not give numbers outside what is on the slide. Yes.
So the ML models that you use for the so a couple of questions about the detectors. A lot of these could be statistical functions, and when you use say ML, what part of it is like neural nets and stuff like that versus statistical, more statistical things.
I understand. So the question is, what part is like machine learning, neural network, CNNs, and what part of it is just like statistics, math, hardcore math? That's a great question. Because the global model that I've mentioned in multivariate is the one that is our deep learning. That is the one that we actually use for the one that has a lot of convoluted networks. Maybe. I don't know what it has actually, but because I'm not a data scientist, I'm a systems engineer. But yeah, so the others are mostly statistical.
Just one more question.
Yes.
It's actually a follow-up to the answer to that question. So you said that, hey, your detectors actually look at the global data, is what you said, right? So if I have a time series, how does the model for some other detector help me when some of the values in the time series for this detector are missing?
Oh, No, it was more of a, so what was the online training and offline training? The question was, what is the difference? So there might be a missing data, there might be bad data, because issues happen all the time. Issues that might happen in the data source itself or the service that is being monitored. So it is possible to train the model with bad data. So offline training also helps us filter most of these things out as well.
Oh.
But like, it's not like a replacement of like the time trees goes missing, if I understood your question correctly. Okay.
Thank you.
Of course.
Yeah, I think this was.
Oh yeah, you're pro at spotting.
I
I
know.
have no idea.
I see the further back when you were first. Go for it. Yeah.
So what is your fundamental guiding principle for Alert Doctor?
What is the fundamental principle of Alert Doctor? So after that was the question is what is why did we do Alert Doctor? Is that a
No, like how do you go in, use the data, and then what are the principles with which it is built?
Oh, I understand. So how do we use the data? So we have the detector configs that exist in the detector's config storage. So this Alert Doctor service basically pulls them as if it's running them to do detection, but instead it basically back tests for a huge amount of time to see if there are any behavior pattern that matches the anti-patterns that we came up with. So Alert Doctor is a platform, you can think, that does this, and it shows the on-call teams or teams in general, oh, these are the detectors you own, these are the issues that I've noticed, and it also manages tasks so that like it does a lot of that. But basically, it's a platform to see if something is wrong and to fix or to track.
Does it have a historical comparison?
Historical comparison. It's yes, but with an asterisk.
All right. There was one in front here. Yeah, right there.
Yeah. So do you, how much do you trust your dynamic threshold? Do you just let it grow with your the scale of your data, and do you have limits so that you know that it's not going to just keep increasing your threshold forever?
So the question is, how do you trust the dynamic thresholds? How do they not cause noise? They actually do cause noise, and they actually are problematic. That's why we are focusing on the ML monitoring side of things. But usually, if there's something, if like a detector is set up badly, and if the user saw the effects of it, we usually get pinged by the user, like the engineer in the company. But we also have our own ways of making sure the models that we train are actually healthy, and they should be trained because we have data available, and we can retrain them. It's a matter of like computation and time. So, yeah. Sorry, I went on a tangent, but like yeah. So basically, did it answer your question?
Yeah, it did.
I want to make sure because I want to say something and then I'm like, wait a minute, that is kind of company secret that I'm not exactly sure. So I want to be on the safer side and not get at a meeting from my
There's
director.
definitely no like legal team standing behind here with like a sniper rifle.
Yeah,
anything like that at all.
No. It's just like I'm trying. This is my first talk, so I'll get there. But yeah. Sorry about that.
Yeah, right up here.
In your slide, you said 50% of incidents are created from alerts. What's the other 50%?
Less than 50% of the incidents are caught by alerts. So what the other type are, you see, oh, my service is down. Like we say less than 50% are caught by automated alerts. So it's like you, an engineer, opening up an issue, that counts as the other side of it, where it's not automated, and you yourself open the issue.
And so your entire presentation is about trying to increase that 50%.
So our goal is to make sure if an issue happens. So the question was, you mentioned less than 50% of the issues are detected with alerts. What is your goal? So our goal is to actually move that metric so that more issues are detected automatically. Yes. So we don't want people to look at dashboards all the time because that's not a good use of their time.
Were there any over here? Or so yeah, right here.
Can you just clarify, is detector something you're monitoring, or is it an agent, or what's a detector?
Oh, sorry. Detector is just like imagine a config object that we build. Our software takes it, and that config gives you your data source, your thresholds, and how you would like to be alerted on. So detector is just a set of configs that we pull up and run, and we call it detectors across the company.
I think you want to know if you had a detector.
Oh, sorry.
No, sorry, that's a bad joke. Right up here.
You mentioned that the offline training that you are doing, you're essentially kind of like cleaning up like data that's bad and like kind of making the data set more useful, right?
That is Not the purpose of it. That is a benefit of it.
Benefit of it. And is that being done automatically, or is that something where you have like a data scientist like engaged in like actually training?
Automatic.
It's automatic.
Yeah. It's a cron job.
Oh.
All right. Make sure I don't want to miss anyone up top. Any other questions? Right here?
Yeah, do you have monitors for the fail-safe, the automated resolution?
I didn't catch that. Can you do that a little bit louder?
Do you have monitors for the automated resolution?
Monitors for the automated resolution.
What is monitors? Do we have monitors for the automated resolution? What does monitors mean? Like, as in, what monitors the monitoring system?
You said there are issues that are resolved by automated systems, right?
Yeah.
How do you have fail-safe for that?
Oh, okay. So there are 98% of the alerts are consumed by automation. There are issues that are solved by automation. How do we keep track of that? I'm not exactly sure. That is another like automated. That is like outside the scope of this talk, and that is not the detection team. That is more of another team that manages that.
All right. Great. Well, so real quick round of applause. Great talk. Loved it. We're going to actually shorten this final break just to kind of keep this thing moving. So that means we will all come back here at 3:30. So 15-minute break. We'll keep it to basically solid 15 minutes. 3:30 we'll be back here for the final talks. Thank you. speaker will be joining us via Zoom, which is kind of amazing actually that with everything going on, there was only one speaker, unfortunately out being sick, but that the other speaker was still able to join us via Zoom. So before we get to that though, I'm really excited for this talk, mainly because I will honestly say, and I'm not too embarrassed, but the slides are all hand-drawn. They're really, really cool slides, and I just love that kind of stuff. Let's give a big round of applause for Monica and Pradeep.
Thank you. Hello everyone. I hope you all are having a great time at Monitorama. We had some great talks about metrics, logs, and traces over the last couple of days. Today we are here to talk specifically about logs. Every application generates logs. No one watches those logs proactively. But when something isn't right, then those are the first thing to look at. Most of you would have experienced a situation where you're looking for some logs and you find them missing and get disappointed. We were experiencing something similar, and today we are here to talk about our experience in scaling our logging infrastructure and how adopting ClickHouse helped us in resolving most of our issues. I am Monica Singh, and I have Pradeep here as my co-presenter today. We work as SRE at Cloudflare in Singapore office. In case we go blank, let's blame on the jet lag. Before we dive into challenges in maintaining these logging pipelines, we would like to talk a bit about the characteristics of logs. In today's world where there are a ton of microservices, the amount of logs that a centralized logging server receives is very unpredictable. There are various reasons why capacity estimation of log volume is so difficult. Primarily because new applications get deployed continuously. Existing applications are scaled up and down automatically to handle business demands. And sometimes application owners enable debug logging and completely forget to turn it off. Another characteristic is logs are semi-structured. Every application adopts different logging format. Some represent it in plain text, others represent it in JSON. The timestamp field within these log lines also varies drastically. Multi-line exceptions and stack traces make it even more unstructured. Such nature of logs add extra resource overhead since they require additional data parsing and mangling. Logs are contextual. Most of the time when we are debugging some issues, we need contextual information before and after an event has happened. A single log line hardly helps. It's a group of log lines which helps in building the context. Many a times we need to correlate the logs from multiple applications to draw the full picture. Hence it's very important to preserve the order in which logs get populated in the data source. Any centralized logging system is write intensive. 99% of logs which are written are never read. They just occupy space for some time and later on get purged by retention policies. The remaining 1% of logs that are read are very important, but we can't predict what that 1% is going to be. So we can't really apply any sampling over these logs. Now that we have looked over characteristics of logs, let's see how a typical logging pipeline looks like. Even though everybody uses different tools to build their logging pipelines, at a very high level, it's mostly the same. Like producers or applications generate the logs, shippers ship them to a centralized queue. Inserters read this queue and write them to a data store. Visualization tools query the data store and let the users slice and dice the data and build dashboards over them. Next, Pradeep will walk us through the challenges with Elasticsearch.
At Cloudflare, we have been running a multi-tenant cluster of Elasticsearch for many years, and it has served us really very well. Over these years, our log volume increased drastically, and while we were optimizing our Elasticsearch cluster to handle such high log volume, we found few challenges. First and foremost, everyone running Elasticsearch must be aware of mapping explosion. Elasticsearch maintains a mapping where it decides how a new document and its fields gets stored and indexed. When there are too many keys in this mapping, it can take a significant amount of memory, resulting in frequent garbage collection. In today's microservices world, every application logs its own set of keys. When you have large number of such microservices, the mapping can easily grow too big, resulting in this issue. One way to prevent this is to make the schema strict, which means any log line not following the strict schema will end up getting dropped. Another way is to make it semi-strict. That means any field that is not part of this mapping will not be searchable, but it will still be stored in Elasticsearch. Elasticsearch does not have a very good multi-tenancy support. One bad user can easily impact the cluster performance. There is no way to limit the maximum number of documents a query can read or the maximum amount of memory a query can take. A heavy query can easily degrade the cluster performance, and even after the query finishes, it can still leave its impact. It is not easy to manage big Elasticsearch clusters, especially those which are multi-tenant. Once a cluster degrades, it takes a significant amount of time to get the cluster back to a fully healthy state. In Elasticsearch, updating the index template means reindexing the data again, which is quite an overhead sometimes. At Cloudflare, we use hot and cold tiered storage. That is, we store the recent data in SSD drives and older data in magnetic drives. While Elasticsearch moves the data from this hot to cold storage every day, it affects the performance during the time when the data is moved. Like any other Java application, Elasticsearch also requires some garbage collection tuning. Default garbage collection in the latest JVM is G1GC. We tried evaluating other garbage collectors like ZGC, which helped in lowering the garbage collection pause a lot, but didn't give us much performance benefits in terms of read and write throughput. Let's now hear about the Cloudflare scale from Monica.
To give an idea about scale at which Cloudflare operates, we serve about 35 to 45 million HTTP requests per second, out of which around 500 to 800,000 requests fail per second. These failures can be due to improper request issues or origin server error, misconfiguration by user, network issues, or various other reasons. These error logs are used by customer support team as the starting point to triage any customer issues. The error logs have vast number of fields ranging from client-side information to server-side information to customer information. It also includes metadata about various Cloudflare products that the HTTP request has gone through. We were storing all these error logs in Elasticsearch. We were heavily sampling them since storing everything was taking a few hundreds of terabytes, crossing our hardware allocation budget for this application. Dashboards built over it were quite slow since they required heavy aggregation over various fields. Also, we need to retain these logs for a few weeks as per the team requirement, which were further increasing our storage needs. Keeping all these in mind, we set very clear goals. First, we wanted to remove sampling completely. That means to store every log line. We wanted to improve fast query support over this huge amount of data. And lastly, achieving all of this without increasing cost. Looking at these goals, the first thing that came in our mind was ClickHouse. We decided to do a proof of concept and see if we can accomplish our requirements using it. So why ClickHouse? Cloudflare has been an early adopter of ClickHouse for their analytics requirement, and we have been managing these ClickHouse clusters. We already had a lot of in-house tooling around it and libraries for inserting data into it, which made it very easy for us to do the proof of concept. Let us look at some of the ClickHouse features that make it the right fit. ClickHouse is columnar database, which means all of the data related to a particular column is physically stored next to each other. Such data layout helps in fast sequential scan even on commodity hardware. This enabled us to extract maximum performance out of our older generation hardware. ClickHouse is designed for analytics workload, where the data has a large number of fields which can be represented as different ClickHouse columns. Most of the databases start performing poorly as the number of columns increase. We were able to design our ClickHouse table with a large number of columns without sacrificing performance. ClickHouse indexes work very differently compared to relational databases. In relational databases, the primary indexes are dense and contain one entry per table row. So if you have 1 million entry in a table, then the primary indexes will also have 1 million entries. While in ClickHouse, indexes are sparse, which means there will be only one index entry per few thousand table rows. This not only reduces the index size, but also reduces the overhead of adding new indexes. ClickHouse compresses everything by default using LZ4 compression. One of the cool features of ClickHouse is you can configure compression per column basis. This feature enabled us to use the best compression for a particular data type. For example, we use special encoding like Gorilla along with ZSTD compression for columns like timestamp. Having an efficient compression not only helps in minimizing the storage needs, but also lets ClickHouse use page cache efficiently. ClickHouse is linearly scalable, which means writes can be scaled by adding more shards and reads can be scaled by adding more replicas. One of the very important features in ClickHouse is it doesn't have any special node. Every node in ClickHouse is identical, and not having any special node helps in scaling the cluster very easily. Having an efficient inserter is equally important as having an efficient data store. At Cloudflare, we have been operating quite a few analytics pipeline from where we borrowed most of our concept while writing the inserter. We use cap-and-p messages as the transport data format since it provides very fast encoding and decoding. Scaling inserter is easy and can be done by increasing the number of Kafka partitions and spawning up more number of inserter pods. One of the key performance factors while inserting data into ClickHouse is the batch size. When batches are small, ClickHouse ends up creating a lot of smaller partitions which it then merges into bigger partitions. The small batch size creates extra work for ClickHouse to do in the background, therefore reducing the ClickHouse performance. Hence, it is very important to set it big enough that ClickHouse can accept the data batch happily without hitting memory limits. Over to you, Pradeep.
Now that we have looked at how the inserter works, let's look at some of the data modeling in ClickHouse. ClickHouse provides an inbuilt sharding and replication without any external dependency. I think there are very less databases in today's world which provide something like this. Earlier versions of ClickHouse used to use Zookeeper for storing the replication information, but latest version removed that too completely. To read data across multiple shards, we make use of distributed tables. It's a special kind of table in ClickHouse world. These tables themselves don't store any data, but acts as a proxy over rest of the tables which are storing the data. Just like any other database, it's very important to choose the right table schema, since it will directly impact the performance and the storage utilization. We would like to discuss 3 ways in which you can store your logs in ClickHouse. The first one is the simplest, but it's the most strict table schema, where you specify every column and their data type. Any log line having a field outside this predefined table schema will get dropped. From our experience, this schema will give you the fastest query capabilities among all. If you already know the list of all the possible fields ahead of time, we would definitely recommend using it. You can always add or remove columns by running the alter table queries like in any other database. The second schema uses a very new feature of ClickHouse, where ClickHouse does most of the heavy lifting for you. You can insert logs as JSON objects, and behind the scene, ClickHouse will understand your log schema and dynamically add new columns with appropriate data type and compression. This should only be used if you have a very good control over the log schema and if the number of total fields is less than 1000. On one hand, it provides you great flexibility to automatically add new columns as the new log fields are inserted, but at the same time, one bad application can easily bring down your entire ClickHouse cluster by misusing this feature. The third schema stores all the fields of same data type in one array and then uses the ClickHouse inbuilt array functions to query those fields. This schema scales pretty well even if you have more than 1000 fields, since the number of columns only depend on the number of data types you are using in your logs. If any of the log element is accessed very frequently, you can take it out as a dedicated column using one of the feature of ClickHouse called materialize column. We would recommend adopting this schema since it provides you the right safeguard against application logging too many fields. One of the other important aspects to get efficient performance out of ClickHouse is how you design your data partitioning. A ClickHouse partition is a unit of data which you can move across one node to another within or across the cluster. One of the common mistakes ClickHouse users do is by selecting this partitioning key too granular, which ends up resulting in too many partitions. Since our logging pipeline generates terabytes of data, we create a new partition at the start of every hour. This way, when we query by timestamp, ClickHouse knows the partition having the actual data and retrieves it quickly without looking at other partitions. It also helps in designing efficient data purging rules. As you know, primary key is very important for having an efficient query performance. ClickHouse stores the data on disk sorted by primary key. Thus, selecting the right primary key not only impacts the query performance but also helps in having a better data compression. Unlike relational databases, ClickHouse doesn't require a unique primary key per row, and we can insert multiple rows with identical primary keys. Having a very long primary key will negatively impact the insertion performance. One of the ClickHouse limitation right now is once a table is created, we can't update the primary key. So it's important to select the primary key early in your proof of concept phase. ClickHouse query performance is directly proportional to whether it can make use of the primary key when evaluating the where clause. We have large number of columns, and obviously all these columns cannot be part of the primary key. Thus, queries on these columns will have to do full table scan, resulting in slower queries. In traditional databases, one can add secondary indexes to handle such situations. In ClickHouse, there is no concept of secondary indexes, but there is a special class of index called data skipping indexes, which makes use of Bloom filters and skips reading significant chunk of data that are guaranteed to have no match. Using all the discussed capabilities of ClickHouse, we built up a new logging pipeline, and we saw overall gain in every aspect. We were able to migrate one of the critical and major log producing application from our Elasticsearch cluster to a much smaller ClickHouse cluster. CPU and memory consumption on the inserter side also got reduced by approximately 8 times. Each Elasticsearch document, which was using around 600 bytes of data, we were able to bring it down to around 60 bytes in ClickHouse world. This allowed us to store 100% of the data in the newer setup, thereby removing the sampling completely. On query side, we also saw huge improvement in the query latency. To conclude the talk, Elasticsearch has served us very well over so many years. Elasticsearch is great for full text search, which ClickHouse doesn't provide. But most of the use cases don't require full text search capabilities. Everyone has different requirements, and you should evaluate what is the best solution for your use case. With that, thank you for listening to our talk, and we are ready to take any questions. Please.
With Elasticsearch, I found that the number of documents by the number of fields kind of determines how many nodes or shards you need in index. Have you found a similar situation with replicas and shards in ClickHouse where the number of documents and or number of fields has an impact on the size of the cluster?
Just repeat the question too for the stream.
Yes. So, if I understand the question properly, with Elasticsearch, based on the amount of the data, the number of shards and replica will change, you are saying? But in ClickHouse, does it happen similarly? So basically in ClickHouse, the main concept is partition, because like how ClickHouse parallelizes the things will depend on how many partitions you have. So you would like to not have too many partitions, also at the same time not too less partitions to get the maximum CPU. The sharding and replication, like those, the concepts in Elasticsearch world doesn't directly map with in ClickHouse world. Hope I answered the question.
Is there an ideal partition size in number of documents and or fields?
Right. In ClickHouse? So the question is there any ideal partition size? It will definitely depend on the size of the cluster, like how much hardware resource, like CPU, because CPU cores you have, because the number of partitions you make, the ClickHouse will try to parallelize those things, and how big is your cluster. Yes, please.
Yeah. I was wondering, did you find that you needed to make any adjustments to tune ClickHouse to be performant at the scale that you're operating at, around like the market cache or any optimization that needs to be run?
So if I understand your question, like did we make any optimizations on ClickHouse clusters to ingest this much amount of data? We have a dedicated ClickHouse team who manages the ClickHouse cluster for us, and they have been managing for many years. One of the optimizations I would like to say is the file system you would like to use. Then basically, as we said, like so ClickHouse completely depends on the file cache, operating system file cache. So if you have a multi-tenant ClickHouse cluster, you will probably not use the file cache in the best way. So we actually gave a dedicated small cluster to this problem. Thank you.
All right. Thank you so much.
Yeah, I feel like another round of applause for those slides because this is fine dog drawing. It's pretty amazing. All right, our last speaker is joining us virtually, so you have to bear with us as we get this plugged in. I do want to see just a quick, not see, but I want everyone to just give a big round of applause for the Portland Center Stage crew that's been helping us out here. Really just fantastic to work with every year. They're really fantastic. There's crew back here that's been helping us out all around the place. Also too, for again, those musical theater fans, rent it's here. I looked like 5 minutes ago. There are tickets still available, 7:30. pretty much if you haven't noticed, they're clearing us out already. Once these talks are over, they'll kick us out, and then they're going to set up for rent. I've actually seen a show here before. They do a really fantastic job. Still seats available. Specifically these 2 seats as well, and well, scattered elsewhere. So highly recommend if you like Rent. I actually don't like Rent, so I don't know why I'm recommending it. I watched the movie and it ruined me. Don't watch the movie as your first entry into Rent. Just go watch actual performance of it. I told Jason he's not allowed to talk about his laptop.
All right, what did we do yesterday?
We plugged it in.
Advanced display center. Oh, where's the mirror? Extend or mirror?
Question from the audience, does the bezel come off? It does, but what Jason has never said is why you would take the bezel off. I still don't know why. What's that? F11? He has not found F11.
No, there's a full screen now.
Hey, Natalie, can you speak? Does any audio come? No, you have to turn your audio on, right? Maybe?
Hey, Natalie, can you do me a favor? Oh, wait. Are we getting audio out? No, it's fine. It's going to be coming out HDMI. Share screen. Full screen. Full screen.
There you go. Well, we haven't solved the talking part.
All right, we're working on it now. Give
Real.
us a sec.
Oh, wait, no worries.
Oh, it works.
All right.
It worked?
Yeah. All right.
Awesome.
All right, well, let's give a big round of applause for Natalie.
Hey everyone, I am really sad to not be here in person with you all, but I did get COVID, so I suppose it's all for the best. So today I'm going to talk about why observability is, at its core, actually just a data problem. So just a little bit about me before we dive in. I'm an engineer at New Relic. I also am a contributor to the Pixie open source project, which we'll talk more about. I love observability and performance stuff. I could talk about it all day, so Monitorama just seems like the best to me. And before I got into observability, I worked in the data space. And that's where some of this will be coming from my experiences working, I worked at a data prep company that helps you clean up and prepare your data and other things like that. So you're starting an observability project. Let's look at expectation versus reality in terms of where the time goes. You may do a little time on setup, then you're gonna do some shiny tasks like making dashboards, adding alerts, automating things maybe, like maybe you wanna update the size of your deployments based on some alert. And then you get to do analytics and ML, which is always very impressive to people. They love to see that kind of thing. But the reality looks a little different. It actually ends up that you spend most of the time, at least in my experience, in the setup phase. I made it in gray because we generally consider this to be more boring work. You spend ages collecting the data. Then you have to get it from point A to point B, and that takes way longer than expected. Then, once you have it somewhere, you actually have to maintain and store this data set at scale. All of these things end up dominating the time we spend on observability, even though it's not the shiny stuff. So, as I said, observability is a data problem. We have, like I said, some of the shiny tasks like data visualization, getting insights from the data, anomaly detection. We always have the dream that there can be an observability tool that will, on its own, entirely root cause my issue, no matter how complex, and machine learning. These are broadly kind of categorized, you can think of it as like the ML and analytics layer, and they always get the attention in the org, whether it's in observability or any other data project. to just hammer this point further, if this is the organization, this is the favorite child. There's a second child, and this does get some attention. There will be someone who comes along saying, well, we have to figure out what we want to measure. What tools should we use? Should we use tool A or tool B? This is still, something that will get some amount of attention in the work. But the thing that seems to get ignored is the glue work. Or it's not really ignored because it's actually where the time goes, but it's not where the glory is. And so this one is the skeleton at the bottom of the pool in this meme that has now been tortured. So this can include things like collecting the data, piping it around, cleaning it up, pre-processing it. You need to give different people different accesses to it. All this stuff, common data problems. And observability data is machine generated, which means it's really big. So scale comes into the picture pretty quickly. You have problems with the performance of telemetry agents. They need to scale efficiently under production level throughput. And this can be a really big challenge when their work scales in proportion to that production level throughput. Resource utilization is often highest at the least convenient times for that reason. Like I said in the previous slide, you have to efficiently store and query this data set. Are you going to do long-term retention? Are you going to sample? Do you have the dreaded high cardinality sources that everyone talks about? And then if you're working in an organization of any medium to larger size, you're not just doing this in a vacuum. You actually have to support and enable dozens of engineering teams. So let's think about what are the 4 stages of any data project, including observability. We've kind of hammered some of these, but let's just outline it for clarity. Step 1 in real life is collecting the data. Step 2 is moving it from point A to point B. Step 3, you gotta store it and maintain it at scale. And then step 4 is actually doing something useful with it. So let's take a look at some advances that are making this data collection problem easier for observability. So a lot of times collecting the right data is actually half the battle. Getting visibility into your application, I can draw the analogy to fighting Hydra. When you cut off one head, another head appears. You may have instrumented your V1 version of your service, but oh look, here's the V2 version of the service and it's not instrumented at all. It can be really hard to capture things like operating system events and third-party libraries. Agent performance is a challenge. CPU spikes, kills. And what we see time and time and again is engineering teams all over the place are all repeating the same work, collecting this same baseline data. The data that shouldn't be any effort to collect in the first place because everybody needs it. eBPF is one tool that you've probably been hearing a lot about, and I do believe it's poised to help solve a lot of these problems, though not all of them, as we'll get into. eBPF programs can provide visibility into anything the operating system is doing, and this means that it brings a lot of use cases. You can do things with networking in it, like the Cilium project, security, like the Falco project, observability and tracing, like with Pixie and Parka. You can see things in the user space, you can see things in the kernel space. Honestly, we're just starting to scratch the surface of everything it can do because it's a relatively new technology in Linux terms. So let's just do a quick dive into how it works in case you've been hearing a lot about it but are not actually sure what it does. You can think of eBPF as like a breakpoint in a debugger. It will interrupt execution when that point in the code is reached. So if I have my application code, I can say, I'm gonna register a probe at when this particular function is called. Then my eBPF program, which I can define, will collect any state that I care about. And this can be state that is used for observability, like how many bytes were sent in that request and things like that. So as mentioned earlier, I work on the Pixie open source project, which is one of the projects using eBPF to help make it easier to collect telemetry data. So it's also 100% scriptable and API driven and Kubernetes native, and it's a cloud native computing foundation sandbox project, which means that it's completely open source and you don't have to use any proprietary vendor to use it. And Pixie uses eBPF to collect rich data sources. It can collect information about baseline things like CPU and memory. It can collect things like network stats, like who's talking to who and what are they saying. It can trace protocols, like trace your DNS requests and see what the request bodies and responses are. Redis, SQL, HTTP. It can collect flame graphs, and it can also allow you to extend Pixie to collect new eBPF data sources on the fly. All of this, because it's using eBPF, requires no code changes, no redeployments, and less than 5% CPU overhead. So let's just do a quick demo and see it in action. I have to hack for a second. That's the COVID. Okay, so I have a GKE cluster, and I'm going to deploy Pixie on it. Because it's using eBPF, I don't have to configure anything. I just run px deploy. And I'm going to press confirm once it tells me I can. But it'll take like 3 minutes to deploy, but I don't want to use the time waiting for this to go. So in the meantime, I can just show you some of the data that eBPF can collect. Okay, so here's another cluster I have instrumented. And right off the bat, we can see a lot of information. We can see, which services are talking to which services. We can see the nodes in my cluster, what their CPU usage is. So let's say we want to drill down into this product catalog service. We can see things like how many requests there are per second. We can see how many errors there are per second. And the thing is this, right? Like everyone needs this information. It shouldn't be hard to get this. And that's why we think that eBPF should be used in this layer, because it's not like some super customized thing that you specifically need. Everyone needs this kind of thing. I can drill down into pods and see the kind of application stuff mixed with the CPU usage and other infrastructure metrics. And one of my favorite features is that I can also see a flame graph of where the functions are taking the most time in my pod. So right off the bat, we can see all this information just running with one command, and that's the power of eBPF. So we think about progressive instrumentation here. It's kind of alluding to it. You have stuff like baseline visibility that should just happen automatically. This could be things like default metrics like CPU, logs, profiles, and raw requests. Then you might want to start customizing this. Like maybe you use a cloud provider and you want to get metrics that are specific to that cloud provider. Or maybe you use Istio and you want to get Istio-specific metrics. So that would be like environment-specific extensions. But at the end of the day, you're also going to want to curate your own telemetry sources that are more business level logic. Like if you're a shoe store, how many shoes were purchased? And so that's where you can actually, combine the kind of automated telemetry that you can collect with stuff that you're manually curating for yourself in your application. So progressive instrumentation, let's just hit it home for a second. So with eBPF, I automatically saw all that information in my cluster, but now I want to collect a new piece of information that's specific to my use case. We can actually use BPF to do that as well. So I'm going to show how we can use Pixie to collect a new data source in BPF. So if you've heard of BPF Trace, it's a flexible framework to write custom BPF scripts in a more, let's say, user-friendly way than classic BPF. So I'm going to show an example of one of those scripts that we can run and start seeing statistics about TCP drops in my cluster. It might be kind of hard to see, but basically this is entirely script-based, and I have my BPF trace script embedded in the script that I'm running. So I'm gonna run this command, it's gonna deploy a new probe, and this new probe is a new instrumentation that I'm collecting. And it's gonna tell me basically where my TCP drop's happening in my cluster. And this wasn't present before, no code changes or anything like that. And right after that, we can see that there are some TCP drops happening in my cluster. We can see, who they're between, and we didn't really have to change anything. We just used the power of progressive instrumentation. And we can also see that this other cluster deployed. So, he is also up and running. But one question is this: does eBPF solve all of my problems? There are some challenges. Challenge one is correlating the events with each other. I might know that these two HTTP events happened, but how do I know that one of them got triggered by the other one? There could be a queue in the middle, there could be all kinds of things that happen in between this one request logically triggering another one. That's where things like trace IDs and structure tracing can come in. Another challenge is associating these raw events with business logic. So this is kind of like the top of the pyramid I was talking about. You may know that this request happened, but it might be harder to translate into how many shoes were purchased. And then also, there is a real problem around ease of development. It is still pretty difficult, even with tools like BPF Trace, to write BPF programs. And so it might be a challenge to learn and write some of those. It might be a lot easier to use other people's. So coming back to our progressive instrumentation period, it's kind of my belief that eBPF is best used at the bottom two layers of the pyramid, and manually curated telemetry is best used at the top of the pyramid for the stuff that's more human-facing. So collect all the machine-generated data you can automatically, and then when it comes to curating sources that have a specific meaning to you, you may want to do that with other tools. So we talked about how eBPF can really help the problem of collecting the right data. Although it does have some limitations, it can be a big step forward. Now let's talk about the challenges around moving data from point A to point B. So this is probably familiar. You've got a ton of agents running, and you have a ton of destinations. And what if they all have to talk to each other? You quickly get into an n-squared problem where you have all these collectors, all these places that need that data, and you have to make each of them talk amongst themselves, and that ends up being more work than a lot of the other things in the first place. They produce, each one probably, its own special Snowflake data format. And each destination probably has its own special Snowflake ingestion type. So then you spend a lot of time just trying to translate these formats of the data from one to the other. In the data space, to be honest with you, the CSV file has kind of served as the kind of universal coordinator of data, where I can take any data source or any tool I want and export to CSV. And I can take most tools and import a CSV. So no matter what, I know I can go in between CSV file. So is there something like that for telemetry data? Because then you go from an n-squared problem to an n problem in terms of the number of connections that you have to support. It reduces the number of conversions. You can easily add a new input type. And you can also analyze all the data together in one place. If I can export a bunch of CSV files, I can analyze them all together. But in order for something like this to work, it has to be a community standard. Because I think we've all heard the adage, there are 5 standards. So I invented a new one to unify them, and now there are 6. Without community support, you can't really actually fix the problem. It will also need to be flexible. So for something like telemetry, you need to support things like metrics, logs, and traces, which are all pretty different. And finally, it needs to be well supported. It needs to work with any programming language you're using, any environment you're using. It can't be something that only has partial support, because that will basically be equivalent to no support. Luckily, the OpenTelemetry project has come in and solved a lot of these problems. It's a common data specification for telemetry. So it defines a format that data that meets the OpenTelemetry specification should match, and then it can work with any tools that use that format. Supports metrics, traces, and logs. But it's also a set of language libraries for emitting OpenTelemetry data so that it's easier to collect this data in the first place. It's also a common API for sending and receiving OpenTelemetry data between sources. And it's also a collector for sending, receiving, and transforming data in the OpenTelemetry format. So it's a really big project with a lot of components. But it's starting to, in my opinion, in the past year, I think that it was always going to be a big deal, but now it's really emerged as the standard. So now, instead of having all of your agents talking to all of your destinations, you can just have the OTel, or that's the OpenTelemetry nickname, collector, work as that kind of train station of data. You can register sources, rules, and destinations. It can transform data for you. And it's all config-based, so it can be checked in like code. So let's do a quick demo of sending data from Pixie to Prometheus using this OpenTelemetry train station. So I have deployed Pixie on my cluster. I need to deploy Prometheus to my cluster. So we're going to do that. I probably don't have to say what Prometheus is, but it's pretty much the de facto metrics database for Kubernetes these days. So I've deployed that. Next, I'm going to deploy the OTel collector. So all that was super easy. And now I'm going to go into Pixie, and I'm going to say, oopsies. Those are actually already enabled, so I'll disable it and then re-enable it. Basically, Pixie supports sending data to any OpenTelemetry source, including the OpenTelemetry connector. So I'm going to enable it, and I'm going to save this. And I can see that these data sets are all being exported to OpenTelemetry. And I can also add my own scripts. Like, all this is entirely script-based, and I can customize the data that's being sent. And this is really the power of OpenTelemetry, because pretty much any tool works with OpenTelemetry. And so now anything that you can send data to OpenTelemetry, OpenTelemetry can send to that other tool. So it works perfectly. Let's forward the port. All right, so we're in here. So we can kind of see the data sources. This Prometheus just got stood up, so it's got pretty recent data, and there's a lot of built-in stuff. And it might take a second for, here we go. So this is this is one of the metrics that Pixie outputs. And it's very small right now because it just got started. But what we can see is that all of this data is now flowing into Prometheus just because of all the power of OpenTelemetry. So I can see things like network stats and connection statistics and CPU and stuff like that, all from Pixie and my Prometheus instance now. All right. Stage 3, storing and maintaining data sets. So it's great. You've got your eBPF, supported data collection. You have OpenTelemetry in the mix, stacked as the train station, and CSV for all of the data that you're sending. But now you have it all in one place, and you're realizing that there is no free lunch here, because it is not free to store this data, and it's certainly not free to query it. So if you go in the most glacially slow data, maybe it'll be 1/10 of a cent per gigabyte per month just to store. That quickly adds up over time, even on its own. But once you get to something that is actually fast, like maybe something like RAM or something like that, then it's like 10 cents a gig, and it starts to get pretty expensive over time. Basically, you can pick 2 of these 3 things: fast, cheap, or complete when it comes to storing your data. You can't really have all 3, unless you have a really, really low bar for what cheap or fast means. estimate of a toy application. So keep in mind that this isn't even that significant of an application. That was basically estimating, based on the logs, metrics, and traces that it was emitting, how much data was that really producing. And the interesting thing that they found was that you would expect that logs and traces to dominate the amount of data that they generated, but it was actually metrics. I guess because they have to export metadata about those metrics, and there's just so many metrics that you can compute. So you end up being that about half of your data would be metrics, and the other half would be logs and traces. Although, of course, it will depend based on your application. So if you have 100 nodes, let's say that this toy application generates this much data. It's a sizable amount over a month. So if you store this all for a year in the fast storage, it can add up to basically like multiple engineers worth of cost to store all that for a year. Now that may be fine for you, but for most people, you probably need to look at how to make that a little more cost effective, especially when you consider the fact that that's not supporting anything like query or transferring the data in or anything like that. Like this is a very, very low estimate. You can sample the data and basically throw 90% of it away. Hopefully you choose the right 90%. That might cut it in half into 1/10, but it might make it a lot less useful in practice. You can do something fancy like store it all in the really slow, but then put a cache in front. Oh, sorry guys, the talking is just hard. Anyway, over time, all of these things will get better. Fast, cheap, and complete will push that Pareto frontier out. And there's a lot in that space doing it. But there always will be a frontier, right? There's no free lunch. So you have to reckon with kind of the raw math of the situation eventually. So wrapping up, eBPF makes it much easier to collect baseline telemetry data. Open telemetry makes diverse telemetry data easier to work with. And there's still no free lunch for maintaining data at scale, but you do have options. Thank you so much. I apologize about the coughing, and I hope everyone had a great Monitorama. Please check out our docs and our open source project, and say hi to the New Relic people in the New Relic booth.
So Natalie, we'll ask the questions from the audience for you if that sounds good.
Oh, we lost. Oh, show it back. Can you hear us? Oh, it's just muted.
It's very cool.
Got my water now.
Oh, that's all right. Well, first of all, I want to thank you, Natalie. I know this wasn't easy. I think it was a fantastic talk, and I really appreciate you kind of frankly, this was a historical talk. We've never done a remote talk of Monitorama before. Frankly, I'm shocked that technology actually works like that. So
yes, considering our luck with just getting the laptops plugged in, there's a lot of complexity.
Sorry, no more IRL Monitoramas, no more dongles. We're going fully virtual.
Yeah.
Just kidding. Never happening. Any questions from the audience? We have one.
For that very trivial use case example you had there, it's just replacing a Prometheus collector. Do you have any information on the performance delta between using the eBPF for doing that versus an hotel versus the native Prometheus collector?
All right, you're good. Pete, you got that right? Jesus, you asked a longer question.
I think it's a short question. I worded poorly.
Yeah. So I believe the question, I'm going to repeat it back if I got it right, is were there performance trade-offs between the eBPF and OTel
versus just native Prometheus metrics?
Versus native Prometheus metrics, Prometheus exporter, I'm assuming is what you're saying, yeah.
Oh yeah, so I mean, if you're collecting metrics that Prometheus already supports, you should totally just use Prometheus. But there's some information that Prometheus doesn't have direct access to because there's no Prometheus metric being exported for it. And so in those scenarios, you may want to collect that data and then expose it as a Prometheus metric so you can have it with all of your other Prometheus metrics. What we see with eBPF is that it has a less than 5% overhead, so it is really fast. And it doesn't really have that much of an overhead because it works directly in the kernel, and there's some guarantees in the verifier that makes it really performant. But I always advocate for doing the easiest thing to get the data that you want. And so if there is a Prometheus metric for that, you should definitely just use it.
Great. Any other questions? Hey, you'll get one back there.
Yeah, so when the flame graph was shown, it had pretty nice symbols. I know that that's sometimes a challenge, but I'm curious how Pixie handles that symbol event for doing flame graphs.
So kudos on the flame graphs. How does, man, I just got the
How
first
does
half.
Pixie handle symbols for flame graphs?
Yep.
There we go.
Yeah, so Pixie looks at the binary, and it currently needs to have debug symbols turned on. And so Pixie just like looks at the binary that is running in the application, looks for the symbols there, and then it can kind of piece it together from there. And we actually have some great blog posts about this topic as well that can dive into it more detail. So if you just go to blog.px.dev and search for profiler, you can get a nicer deep dive into that topic.
Awesome, thank you. Any other questions? Anything on the top? Do you see any, Jason?
I don't. If you have any more questions, feel free to ping Natalie in the Talk Natalie Serino channel. But again, thank you very much, Natalie. Appreciate it. Great way to close out the event. So thank you very much.
Thank you so much. And before you go, Natalie, we're going to attempt to turn you around.
Hold on, we'll let you see the audience.
Yeah.
All right, I have to disconnect the video, but just so you can see.
There's actually an audience. Everyone wave, everyone wave.
Thank you, Natalie. Have a good one. Hope you feel better. All right. Woo! Technology can't work. All right. Let's see. I have a few closing notes. I just want to say thank you. Well, obviously, thank you to everyone for coming to the event. Frankly, I keep doing this because I keep getting really great feedback from everybody. I mean, when you stop me in the hallway, if it looks like my hair is on fire, it's probably because it is. Frankly, I appreciate both the criticisms, the critiques, as well as the positive feedback, so please keep it coming. We'll be sending out a survey in the next week or so, so try to get your feedback while it's still fresh. Okay, I have some notes. Wow, apparently I forgot to hit update secret gist. What could go wrong, right? There's no chance that I lose this on conference Wi-Fi.
Oh, you thought I was joking about the conference.
Okay, so, and to express my gratitude for y'all sticking around for a full 3-day conference, we do have some giveaways. I know folks have been very interested in that. So hopefully you grabbed your socks and you gave us half your ticket, because that's what we're going to be picking from. All right. First, I want to say a few notes, and then we'll do the raffle as quickly as we can. I just want to say a few thank yous really quickly, if that's okay. One, to all of you for wearing your masks. I know it's for a lot of us, including myself, is the first in-person event that we've been to in years. And so being able to do this in a safe and sane way was really important to me, and I think to a lot of you. So thank you very much for your support, for your cooperation. The venue itself has said, just raved about the compliance here. So thank you very much. Obviously to our speakers. For me personally, you're giving me a reason to do this. You're why our audience flies all over the world to be here. And frankly, again, it's where I find the motivation to keep putting on these events. So quick round of applause again for all of our speakers over the last 3 days. To our sponsors, our diamond sponsors, platinum sponsors, and silver sponsors. I don't have time to list you all off, but I'm very grateful for all of your support. You've allowed us to, obviously have this event, to be able to put it on, do great things for our attendees, and to continue to innovate in this space, both in software and logo design. So thank you. to Nosa Familia for their coffee and their merch, some of which you'll be getting hopefully soon. To Searle Video, to Paul and his group in the back row there. He's been with us basically since the beginning in Portland. Well, I mean, after I decided that I'd had enough of trying to do it myself. So that team does a fantastic work with the video capture and the live stream. To Artemis Catering, they're probably not here anymore, but they did a great job with the food and the snacks, especially the masala popcorn. I don't know if anybody else got to try that, but that was dope. Sorry, kids. To the PCS, Portland Center Stage staff, and I thank them every time, but it's true, they act as our silent partners, and they're literally the backbone of this event. I couldn't do it without them, so thank you very much. And to our volunteers, to this guy, Mr. Pete Cheslock, who stepped up and has the energy sometimes that I don't, so I really appreciate it. You're a good friend and a, well, I won't say a better MC, but you're a good friend and an MC.
Can't beat Will, man. He's good. Keep it motivated.
And most of the folks, we had volunteers that helped out with all 3 days. Some of them were not able to make it all the way through, but to Danielle, Molly, Brad, Jordan, and Nicole, who did literally everything else and who freed me up to run around with my hair on fire. Thank you to all of you. And last but not least, to my family. I don't know if my wife, I think she's hiding backstage, but to my wife, who puts up with me and supports me silently behind the scenes. And to these two, Nathan and Alyssa, who I think a lot of y'all met at the coffee stand. It's wild. Like, we've been doing Nosa Familia pour over stuff at this event, I think, since we started. And that's a service they no longer provide for obvious reasons. And to have these two step up and be professionals and help us with that is pretty cool. So. I think that's all I've got. So.
I want to thank Jason because he's clearly not going to thank himself, but we should do a big round of applause for Jason because he does put a lot of his time into this event and he's knocks it out of the park every year.
I'm very uncomfortable with praise, Mr. Cheslock.
Welcome to the club. So we've got a lot of stuff. We're going to try to run the things to you. We're gonna do it at random, so don't all the good prizes are gone. I'm gonna get stuck with one of the 300 bags of coffee here. We're gonna do it at random between. It's all coffee.
Okay, I just want to say, we've got some really good stuff. If you don't drink coffee and we call your name for coffee, just let us know and we'll swap it out. But there seem to be a lot of people that are interested in the coffee, so hopefully you're one of them. All right, we're gonna start this off. What will we do first? We're gonna start with a bag of coffee. All right, and by the way, it's ground by Nosa for V60. So 483. Wait, I don't need to pronounce all of them, right?
That's a really hip way of saying it's a drip coffee grind.
Yeah. 483. It should work like in an automatic.
So check. I think we're gonna do last
7. All right, I'm gonna do the last 4. Yeah. All right, for now. 7609.
Got it right here.
Right there.
Yeah, keep your hand up. Bring it to me. What's that?
All right.
Another coffee.
Chat. How about? Yeah, one more coffee. One more coffee. 7790.
7790.
Anybody?
We got it.
Oh, you got it right there.
Oh yeah, here we go.
Yeah, awesome.
Shout it out! Come on, this has got to be like the Price is Right. We got. All right.
All right. Travel mug, Nosa Familia.
It's called an e-coffee cup. It is not electronic.
I think it's like a keep cup, but they probably couldn't license it. 7843. Anyone? No? Okay. If you have your hand up and I don't see you, just yell.
The light is really bright.
Yeah.
So
7716. I would say with yell and hand, maybe.
Oh, we got it.
All right. 77s. Oh, what are we doing now?
Do the hat because I'm just holding on to the
All
hat.
right, the hat. 7771.
Yeah.
Nice. All right, coffee.
You want coffee?
Yeah, coffee.
There's only 8 left.
There's 9. Wait, no. 8. All right. That's a lot of coffee. 7653. if your hand's up and I don't see you, just yell.
If you don't know what to yell,
Yeah.
yell Kubernetes.
7627.
I didn't hear Kubernetes.
All right. Okay. So. All right. So that's the small. Okay. So we have these really nice sweatshirts from NOSA. One's a small, one's a medium. We're going to call this one out, and you get your pick of which size you want. And if you don't want either, you can have a bag of coffee. 8054. Going. 8000. I heard somebody? Okay, what do you want? Small, medium, or coffee?
Small.
Small? Awesome.
The other one?
Coffee.
Don't threaten me with a good time, Jason.
I take that back. All right, no, we'll do the medium. Medium or coffee? 7895. Coffee?
Coffee? All right.
All right, medium or coffee? 7701. I can't tell if you're raising your hand. Get your badge cut out of it. It's not an auction. All right. 8036.
Keep looking at my ticket instead of the crowd.
Nobody? Okay. 7746. Going faster now.
Oh.
7848. 7885. 7610. 7977.
There we go.
Medium or coffee? Medium. Yeah. All right. Let's do one of the. Yes. These are quite nice.
These are really. It's a shame there's only 2 of them.
77. There was 4 of them, but 7772. Nice. Yeah. Okay. So
there's some good stuff.
this is a bag containing items that basically like my favorite things from Portland. I mean, short of Salt and Straw and Blue Star and the venue
And the 300 other things you love.
Yeah.
We've got Jacobson's Salt Company, a lot of different salts, really delicious stuff.
The black truffle salt.
Kova instant coffee. You're gonna say instant, that's really weird. This is like
Really
next
good.
generation instant coffee. And then Stephen Smith variety tea. So just
Smith
really
tea maker.
fantastic.
It's excellent. All right. 7971. 7842. Wait, do we got one? Or is my son just running up the stairs? All right, you got it?
All right.
I didn't say, I couldn't hear you. All right. Okay, let's do another cup. Cup. How many bags we got? All right. 7685. Okay, next. 7915.
Oh, I see
Back
one.
corner. All right, coffee.
Coffee.
7794.
Kubernetes. Coffee it up? What do you want to do?
Yeah, let's do another one. 8065. You got it?
No.
Oh.
I didn't see it.
7597. $7899. Bring that back. All right, coffee. 7907. No? Okay. 7595.
Yes, I heard something. Oh, up top. We'll set it aside.
Do not throw that up there.
Another coffee.
Another coffee. 7534. 7955. 7959. 7571.
I heard one.
Where?
Oh, way in the back.
All right.
Great.
We still got coffee.
Yeah, there's 3 coffees and 3.
Beautiful. All right. Yeah, coffee cup. 7963. 7553.
There we go.
All right, coffee.
Coffee.
8080.
8080. All right, coffee. We want to do a bag?
Yeah, bag. 7858. 7840.
Was it up top?
Up top.
Okay, yep, we'll hold it for it.
Yep.
Coffee.
7887. Okay. 8056. 7575. 7847. 8079. 7916.
Oh, I heard something. Straight back, yep.
All right. All right, what was that? That was coffee?
What was that? That was coffee. Oh, yeah, so cup.
Where's the cup? Oh, she's got the cup. Okay. 7983. 7570. All right. Is that
Last
it?
one, last
we got
one.
one coffee? We got a coffee, okay. 7564. 8046. All right, coffee right there. Is that it?
That's it.
Raffling off a bag of used raffle tickets. Thank you very much, everyone. I hope to see you again. Matthew, if you're in the house, I'd like to give you your dongle back.